So good evening, all of you. So clear audio and video is clear. Okay, right. Srishti, you try that question. Okay, try that and send me in the Telegram. I will check and send you. Okay. So last class we started about performance of transformer. So to know the performance of transformer, we have two parameters: efficiency and voltage regulation. So in terms of efficiency, we required a high efficiency so that transformer is good one. But in terms of voltage regulation, it should be as much as possible low value. Low regulation indicates less or low voltage drop within transformer. See, our main aim is whatever EMF is induced, that should go to load terminal. But if most of the voltage drop within the windings, that is not desirable one. So we need mostly voltage to load side. Mostly it should not drop within windings. So voltage drop should be less, which means that the voltage regulation of transformer should be as much as possible low value. We prefer that. Okay. Now this regulation mainly depends on what types of loads. We are connecting different loads. Transformer is not designed to operate it only at some particular power factor, or not in order to supply only some particular load. You can connect any type of load to the transformers. So in our home example, we have different types of loads like geysers, that is heaters. Heaters, we have induction stoves we have. So there are so many types of load, motoring loads, compressors, ceiling fans, are different types of load we are connecting. So any type of load you can connect to transformer. Okay. But based on the different types of power factor, now we will calculate what happens to voltage regulation of transformer for lagging power factor, leading, and UPF. For different cases, we will check now what happens to regulation. Now, what is the need to know about regulation? Suppose if you know this much is the voltage regulation of transformer, or this much voltage drop in transformer, so that we will increase some more number of turns there, so that that voltage drop may compensate. For that reason, anything we should know. So we should know the transformer voltage drop is this much when you connect this load. So we have to increase some more turns. And if you remember, mainly in the substation transformers, we have tappings. Tap changer transformers will be there. What is the need of the tap changer is whenever load is very high on transformer, mainly under summer, during this summer duration, as loads are increasing, then voltage drop will be more little bit in transformer. Then to compensate that voltage drop, they will use the tap changers. Tap means they will increase some number of turns. So they will keep without any operation that number of turns generally. So whenever it is required, they will increase the number of turns so that little EMF increase and little voltages will compensate whatever drop is taking place. That is tap changing transformers. tap changers we provided. Okay. Yes, right. Okay. So first we have seen in the previous class about lagging power factor. We have seen about lagging power factor previously. If load on transformer is lagging, means RL type of load, what happens to the regulation? Is it positive or zero, negative? We need to check. Positive means how much voltage or how much regulation that is, or how much voltage drop that is. So that is we are calculating. So we have seen that one. This is the equation for voltage regulation. Percentage R cos phi plus percentage X sin phi. Now make a note below this equation. Make a note. See, manufacturer cannot design like at maximum efficiency rating always, because manufacturer know that this transformer is going to operate for this type of load. So manufacturer doesn't know anything. He will keep in mind while designing only two things: copper and core. That is copper loss in the windings, core loss in core taking place. So based on that heating produced, they will design only based on voltage rating, current rating, and they never consider about power factors there. So this transformer is going to operate at any power factor. Any power factor it can operate. Not only transformer, alternator also same. The rating of alternator also in volt ampere only, like 100 kVA or 100 MVA or 10 MVA in different alternators. Power generating plants we have, the rating is MVA, megavolt ampere. That is not in watts. Only induction motor ratings, motor, DC motor, induction motor. So these ratings we give in watts. So some induction motor, 1 HP motor or 2 HP motor or 1 kilowatt motor or 2 kilowatt motor or 10 kilowatt motor. Like this we give for motors. But alternator and transformer volt ampere only, because these two we never design by considering power factor. Only voltage current we will consider, so that it can operate at any power factor. That is not a point here. Okay. The construction parts are same for power transformer and distribution transformer. Particularly, if you observe in distribution transformers, mostly we don't have that. In some of the transformers, they don't use conservator and all, because low rating there is no big problem. But if you go to power transformers, there definitely we should have conservator, breather. But if you observe outside distribution transformers, breather also will not be there. For most of the distribution inverse states also, breathers they don't place there. For small distribution, breather also they don't use, because these are all maintenance is increased. To reduce that maintenance cost, they don't put all this conservator or breather. But for power transformer, if you visit any substation, there definitely for the transformer, it will be there. Conservator, breather, everything. Okay. Synchronous motor also they will give in volt ampere mostly, because there are some capacities motors we designed. Synchronous motor particularly can operate at any power factor, lag, lead, UPF, any power factor synchronous motor operate. That's why the rating of synchronous motor also volt ampere only they give. Okay. Only induction motor, DC motor we have in watts. Power transformers will have high efficiency compared to distribution. Okay, make a note below this. So yesterday we completed this case 1 in the voltage regulation. So those who missed at the last, just take the snapshots. So this voltage regulation is three types: zero regulation, positive regulation, negative regulation. Okay. Now this positive, zero, negative depends on what types of loads. That's why we considered first one. If load on transformer is lagging power factor, then for lagging power factor, what is the regulation? We got positive, because E2 magnitude from the figure you can observe magnitude of E2 greater than V2. This is V2 and this is E2. Magnitude E2 is greater. That's why regulation will get positive, because difference we need to check E2 minus V2 difference. Positive regulation it is. Okay. And the value of that regulation, how much means this much percentage or cos phi plus percentage x sin phi. So this is for lagging we got. So make a note below this equation. Note the percentage regulation is equal to percentage or cos phi, percentage or per unit. Sometimes they will ask per unit regulation, then per unit resistance cos phi plus percentage x sin phi or per unit x sin phi. This is plus or minus I am taking here. Remember this equation. Plus is used. Take plus for lagging. So lagging we got plus only. Use plus for lagging power factor whenever given in any numerical. And use minus whenever given leading power factor in the question. So there we get minus. Okay. Again, I'm not deriving for again leading power factor. So just take minus for the same equation. Leading power factor it is. And then what is the regulation for UPF? UPF regulation. So that I will give in the next case, case 2 anyhow. So I'm not writing. Remember this equation. Direct questions on this equation based on the lagging or leading or UPF you will get. Next, case 2. Today we complete mostly the single phase transformer. With this regulation topic, single phase will be completed. After that, we start non-linearity, operation of transformer with non-linearity. So that is the most important further to understand three-phase transformer very well. Okay, right. Case 2. Case 2. If load on transformer is UPF, if load on transformer, if load on transformer is UPF, unity power factor load, means purely resistive load. Unity power factor load. Suppose if resistive loads are connected, what will be the regulation of transformer? We need to check. Same procedure, whatever we have taken previously, case 1, this equation. For the same equation, now also we draw phasor diagram. Same procedure. V2 is reference, first V2. Then as it is UPF, current I2 will come in phase with V2. And then resistance drop parallel to current, reactance drop perpendicular to current. Then the resultant of these three vectors will give E2. Okay, same as it is, we will try again. The equation is E2 equal to V2 plus I2 R02 plus J I2 X02. Same equation we are drawing phasor diagram for UPF flow. Now considering V2 as reference, V2 is reference. Okay. Now what is the load UPF? UPF means our resistive load means current will be in phase with voltage. So let's take the current I2. So whenever load connected, I2 will flow. That current I2 will be in phase with voltage, both in phase. because of resistive load it is. Previously lagging, so current lags. Now UPF, both in phase. Whenever there is a current, resistance drop will take place and reactance drop will take place. Now let's draw resistance drop from the voltage vector parallel to current vector I2 R02. Okay. Now where is the reactance drop? Perpendicular. Reactance drop, resistance drop always perpendicular. So this is our reactance drop I2 X02. Now join this, you'll get the resultant. E2 is what? V2 plus resistance drop plus reactance drop. So these three, this is our resultant. E2 it is. Now check from the figure, check again. Regulation is positive or negative or zero, we need to check. What is the regulation? Proportional to, regulation is E2 minus V2 by E2. So it is proportional to, numerator is what? E2 minus V2. If E2 is greater than V2, you will get positive. Again, from the figure, check the magnitude of this E2 greater than V2 only, no? Up to here V2, and this is E2. So E2 is greater again compared to V2. Therefore, the regulation at UPF also positive because E2 is greater than V2 from the diagram. Positive only we get for UPF. But what is that value? Less than previous case or greater than previous case? Positive regulation. E2 minus V2 is greater. E2 is greater than V2. How much positive? Now, greater than previous case or less than previous case? Less than previous case. Okay, why less than? Observe the previous diagram once. Observe the previous diagram. Whenever current is lagging, check what is the magnitude of E2. It is so greater, no? It is more greater than UPF case. This much is the E2. Whenever current is lagging, this is the magnitude of E2. So consider V2 is fixed one, same value V2. Now E2 is very high. Then what is the difference of E2 and V2? More value. So regulation is more positive for lagging power factor. Now check for UPF. Previously I2 is here, lagging case. Now whenever current is moving in this direction, I2 R02 also moving in this direction. So we got like this, and I2 X02. Then the magnitude of E2 reduced or not? Yes. Whenever little E2 reduced, what is the difference? Also reduced. So regulation is positive, but less than lagging power factor. Less than lagging power factor. Suppose previous voltage drop is 10 volts. Now how much voltage drop here? Yes, it is positive, but less than that, maybe some 6 volts or 7 volts. Like that, regulation is positive only. And how much regulation? What is the equation for this? Percentage regulation is equal to percentage resistance. Same equation I'm writing like previous equation. See, same previous equation. This is utilizing again percentage regulation for UPF is only percentage R. Why only percentage R? See, substitute in this equation. If it is UPF, UPF means cos phi is 1. So percentage R into cos phi 1 UPF plus or minus anything if you take also percentage X. What is sin phi? 0. Why sin phi 0? Cos phi 1 UPF 1 means what is the angle? 0 degree. Both in phase, no, current and voltage. Then what is sin 0? 0. That's why you will get only percentage. So for UPF, what is the equation of regulation? Only percentage. Remember, this is the magnitude of regulation at UPF. For lagging, take plus, same equation. For leading, take minus, same equation. Okay. Completed all of you this. Now, like this same way, you try to draw for leading power factor, case 3. Case 3. If load on transformer is leading power factor. Important. Case 3 important. Case 3. If load on transformer is leading power factor. Leading power factor means RC type of loads. RC. Then what will be the regulation under this leading power factor? Again, same equation. We are drawing phasor diagram. I2R02 plus JI2X02. Same equation. But in this case, again, we have three subcases because I will show you now slowly what happens. Observe now. Observe carefully this diagram. Here only I will explain and then I will go to third case. See, leading power factor means what should be the current? Voltage is fixed, reference. V2 will not change, fixed. Now current I2 little shift in this direction. Current I2 leads. Now current I2 leads. Whenever current I2 is leading like this, step by step, this is in phase, I2 leading, and so on. Whenever I2 is moving in this direction, I2R02 also will come like this. I2R02 also will come like this. Then I2X02 will come in this direction. So whenever I2X02 is moving like this, the magnitude of E2 will reduce or not? Yes. So slowly E2 will reduce. So at that time also positive. See, up to some value E2 still greater than V2. So positive regulation only. But whenever still I2 is moving in this direction, slowly E2 will reduce and becomes equals to V2. E2 equal to V2. Then what is the difference of these two? Zero. So zero regulation we will get in the leading power factor only. Like that, if you still move the current towards leading, E2 value still reduce, then you will get regulation is negative. So in the leading power factor case, we are getting three types of regulations. Positive regulation will be there, zero will be there, and negative also will be there. Now with these three sub cases, I will show you how it is positive, zero, negative. Check it is. First sub case. Again, first one in this. Now first I will take leading, current lead. So just lead I will take. This is V2. Current leading power factor. No? Now previously UPF in phase. Now I will take just leading, current I2 just leads, leading power factor. So I2R02 parallel to current. I2R02 parallel to current. Okay. I2R02 parallel to current. Then I2X02 perpendicular to resist. I2R02 is perpendicular. I2X02. Therefore, the resultant of these three vectors is we call E2 now. Now, what happens from previous case UPF? Compare previous UPF and this case. E2 is still greater than V2 only. From this diagram, E2 still greater than V2. Okay. Then what is the regulation you get? Positive only. No. Difference you will get positive. So regulation is positive. But less than UPF case. Because E2 still reduces. So like that, let us take second case. So like that, whenever current is still leading like this, at one of the power factor, E2 will become V2. Then regulation will be zero. So that is our second case. Let this is V2. Now I will take current little more leads. Now at one of the leading power factor here, so I'm considering approximately E2 equal to V2 in this case, I2R02 and I2X02. So approximately check the diagram. This is E2. So approximately the magnitude of E2 and magnitude of V2 both are same. E2 is equal to V2. Therefore, as E2 is approximately equal to V2 now, then what is the difference of these two? 0. So regulation we will get 0. Okay. So like that, whenever current still lead now what happened? E2 still reduces. Then difference you will get negative. So like that, three types of regulation possible for only leading power factor. Now what is the regulation for previous two cases? Positive only. But only in leading you are getting a positive regulation, now zero regulation. And if you take third case, you will get a negative regulation also. Now let's take the third case. Now current is still leading. Suppose this is V2. Now I will take current little more leads. This is I2. Okay. Now I2 R02 parallel to this I2 R02, and then I2 X02 perpendicular to this I2 X02. Then the resultant of these three is E2. Then if you observe here, this magnitude of E2 becomes less than V2. Magnitude of E2 is what? Less than V2. Therefore, what is the regulation? You will get negative. Now you will get negative. Okay. Clear all of you this? Why it is becoming positive, zero, negative? Same for alternator also. If you learn well here, alternator also same thing. With the lagging, leading, same up to these three cases. Okay. Oh, lakhs are least, that is not a matter. Don't consider about E2, I2 here. So we are checking only E2, V2, that's it. Whatever it is, lagging or leading, whatever it is, because we are not drawing with any exact values. Just I'm showing whenever current is leading, then you will get regulation, different types. That's it. In all these reference diagrams, we are considering voltage V2 as reference. V2 we are taking reference in all the diagrams, not only this, in all three cases, V2 we taken reference. Okay. So three types of regulations we are getting: positive, zero, negative. Yes, regulation zero means no voltage drop. E2 equal to V2, that is. Zero regulation is what? E2 equal to V2. See, when terminal voltages will increase, actually, what is the loads we are connecting always? Lagging power factor only, practically lagging power factor. In lagging power factor, what is the regulation we got? Positive. Positive means lagging and UPF, both cases. Positive regulation we got. Positive means E2 greater than V2. So practically this is only will be there. But when you connect capacitive loads, okay, at that time, so RC, leading power factor case 90 is leading means what? RC load means capacitive loads are included, but capacitive loads very rare, we don't use. Whenever you connect this type of capacitive loads, then receiving end voltage will generally increase. Maybe in transmission lines we have loan shunt capacitors. When you connect shunt capacitor, terminal voltage will increases. Voltage improvement methods: shunt capacitor, if you connect, terminal voltage will increase. Then receiving end voltage is greater than sending end voltage, then that is a negative regulation. Same thing. However, there you will see in the transmission lines voltage regulation, here also it is same. So terminal voltage will become greater than this sending end voltage. Sending end voltage is what here? E2, EMF in the winding. V2 means terminal voltages. So when you connect capacitive load, terminal voltages will rise. That's why we are getting this negative regulation in leading power factors. Okay. See, actually this negative regulation means terminal voltage is greater than sending end, then power will reverse means actually load will consume power. But in this leading power factor case, whenever terminal voltages are greater than sending end voltages, then power is sent back to source, power is regenerated. But that is not desirable. No, transformer should supply to the load. Transformer will not take from load again. Then, but why we are calculating all this? So that to avoid these problems, if you know at which power factor transformer will give negative regulation and at which power factor transformer will give zero regulation. If you know this point, you never operate transformer at that point. Suppose I know that at this 0.95 leading power factor, this transformer giving zero regulation. Okay, then I never connect this power factor. I never connect. I will connect above that only, like UPF loads or 0.9 lagging or 0.95 lagging. So there only I will operate. So we should know where we have danger so that we will avoid the operation of transformer at the danger point. For that reason, we are calculating, we are knowing all these points. This is not required for us. We don't want negative regulation and we don't want zero regulation. We want positive regulation always and small value that is. For that reason, we are knowing all these points so that we can operate transformers safely. Okay, don't think anything uh, other than this, because people are asking, is negative regulation is required or zero regulation is required. So don't think like this. To build the subject, whatever is required, think up to that only and not beyond that points. Okay. Yes, Ferranti effect. During that Ferranti effect, we will get negative regulation. Receiving end voltage greater than sending end voltage. No, that is due to capacitor effect only. Okay. Okay. Next. So these three types of regulation for leading power factor. Now all these cases. So whatever we have seen, three cases: lagging, leading, UPF. Three cases. And what is the equation for leading power factor? For leading power factor, what is the equation? Percentage regulation is percentage R cos phi minus percentage X sin phi. Take minus in the same equation. This is for leading power factor. Percentage R cos phi plus percentage X sin phi for lagging, and for leading take minus in this. Zero regulation is good or bad? Tell me. Zero regulation is good or bad? That is the critical point. Why critical point? Yes, zero regulation good. So according to your point of view, means you are thinking that zero regulation is no voltage drop. E2 equal to V2. Yes, that is good, no doubt. But there is a chance that if little variation of power factor in leading at that time, there is a chance that V2 will become greater than E2. Then power is sending back to source. No, the regeneration is may be taking place. So that is not preferable. Okay, receiving end voltage should not be greater than sending end voltage. Otherwise, if receiving end or load end voltages are greater, your loads may damage. With high voltages, your load insulations may damage. So to avoid that problem, we never prefer to operate at zero regulation. Okay, so we are knowing where we are getting zero regulation so that we will avoid the operation of transformer nearly that. Otherwise, if little change occur at that time at zero regulation, receiving end voltage will become greater than sending end voltage. If it is high voltage, the loads will damage. Okay. Yes, just like marginal stable. Yes, like Ferranti effect. Okay, anyhow, so all these three cases now I am drawing in one curve or one graph, that is we call regulation curve. So this is 100% same for alternator also. Okay, so I'm relating so that you will get very easily understand whenever it is there alternators. Okay, same as it is transformer it is, right? Side heading regulation curve. Regulation curve. So all three cases in one graph. Whatever we have seen, all three cases in one graph, that is regulation curve. Observe this. So taking on y-axis regulation magnitude, positive regulation here and negative regulation here. And on x-axis considering power factor. Different power factors we have UPF, lagging, leading. So at the center of this graph, we are considering UPF. Okay, and one side lagging, other side leading power factor. So this is considering as lagging power factor region, and this side leading power factor region. Okay, 0 to 1 power factor range, lagging or leading anywhere that is. So this is one UPF at the center. Then let 0.8 lagging, 0.6 lead lagging, 0.4 lagging, 0.2 lagging, 0 power factor lag. Like that in leading case also, 0.8 lead, 0.6 lead, 0.4 lead, 0.2 leading, and 0 leading. So different types of loads. So if you indicate with the load elements, what is the load here? Resistive load, purely resistive load, UPF. Okay, now what is this load here? RL load. And what is this load exactly at 0 power factor? Means purely inductive load. 0 power factor means either purely inductive load or capacitive load. Similarly here, this is RC load, and here purely capacitive load. So all types of loads in x-axis. Now first starting from UPF, what is the regulation at UPF we got? Positive, no? See, regulation at UPF, second case, positive. Regulation is positive. So some small value positive it is. So positive, some marking, positive regulation, some value. Now if you move from UPF to lagging this side, what happens to regulation? Increases or decreases? So you can observe from graph also. See, this is UPF case 2. There is some positive value here. If you move to lagging from UPF, check what happened. See, this is UPF case here I2. Now when you move towards lagging, suppose I2 is moving like this, then what is the magnitude of E2? Increases. I2, E2 increases, E2 increases. Then what is the difference? Also increase. So regulation increases from UPF. Regulation increases if you move towards lagging power factor. Increase, 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 and reaches maximum at one of the power factor. So somewhere nearly that 0 power factor, it will reach maximum regulation. Not at 0.1. So it is 0.1 according to our graph. Not at 0.1 always. Nearly 0 somewhere. Maybe at 0.1 or 0.2 or at 0.15. So somewhere you will get maximum regulation. This is the maximum regulation. Now let's move from UPF to leading case. UPF to leading. This is UPF, current in phase. Now current is lead, and so on. Then what is slowly that regulation? That positive regulation at UPF slowly become 0. So it will reduce to 0, and then it is negative. This is the regulation curve. This is regulation curve. Okay, same curve for alternator also. 100% same curve. Same variations, there also same variations. The only difference in that alternator equation is here we are writing E2 equal to V2 plus resistance drop plus reactance drop. But in alternator, same as it is, we write like EMF in generator, terminal voltage, armature resistance drop plus synchronous reactance drop. Same equation it is. Just similar to our transformer equation. But here we are writing E2 equal to V2 plus I2R02 plus I2X02. Same. Okay. Now, there are some important questions directly you may get from regulation curve, particularly for COM-T2 examinations, your state electricity boards and engineering service and ISRO examination, any PSU may ask directly from regulation curve. Very important it is. And one important observation you have to do here is, check the graph. This graph or curve is symmetrical or unsymmetrical. Symmetrical or unsymmetrical? Yes, this is unsymmetrical. Means with respect to zero of this regulation, is the positive peak and negative peak are having same magnitudes? What is symmetrical signal means? Like this. Symmetrical it is. And what is unsymmetrical? Like this. Is it having same positive negative magnitude? No. This is unsymmetrical and it is symmetrical. So regulation curve is a unsymmetrical curve. That is important observation. It is a unsymmetrical curve. Okay. Now we have to see mainly in this curve what is the condition for this zero regulation. We have two conditions. From here only you will get numericals. Condition for zero regulation, where we get zero regulation, at what power factor you will get zero regulation. So mostly that zero regulation you will get between 0.9 and UPF. So this is let 0.9, 0.9 and this is 1. Between these 2 points, between 0.9 and UPF, your regulation mostly will become 0. Okay, most of the cases, zero regulation between the 2 points you will get. Remember this. And we have to find what is the condition for maximum regulation. At which power factor transformer will give maximum regulation. So maximum regulation is required, not required. Then why we are calculating? Yes, if you know, here you will get maximum drop or maximum regulation. So we will avoid the operation of transformer here in these power factors. At 0.2, 0.3, 0.4, we don't operate because drop is more there. So like that. And zero regulation. Why we need zero regulation? Yes, if you know that at this power factor your transformer is giving zero regulation, we never operate nearly that, because if you operate nearly that, there is a chance that to cross that limit, that is it may go beyond zero regulation, that is negative regulation may get. So to avoid that problem, we will find maximum regulation condition, zero regulation condition, so that in between only we operate transformers. Okay. Now before going to conditions, let's see some small questions. Why the curve not starts from origin? So what I can tell for this, Shiva? Why it is not starting from UPF here? So this is not our wish to draw directly at origin, no? Because why we are drawing from here? We know at UPF what is the regulation we got? Positive value. Then how can you take at zero? We cannot take, no? So according to our data we got, we are drawing that may be going through origin or may not be going through origin. But it is not going to origin because at UPF regulation is positive, not zero. In leading power factor somewhere it is zero. So I shown clearly in the phasor diagram all. Okay. Yes, practically loads are lagging only because overall loads, if you take load means not your home load, no? On transformer, the load on transformer means, is it only your home load? Only your home is the load? No, There are some number of maybe 10 homes or 20 homes or 20 houses like that. So a particular, if you calculate the resultant of all these power factors, it will be under lagging only. Okay. Ideal transformer practically doesn't exist. So don't think of that. So ideally for our calculation, we are considering like ideal, but practically it doesn't exist. Practically the regulation is less 3%, 4% positive value. Yes, we never operated reading. Okay. See the question. Question. A transformer, a transformer having a regulation of transformer having a regulation of 12%, 12% at 0.8 lagging power factor, at 0.8 lagging power factor. What is the regulation? What is the regulation at 0.8 leading power factor? At 0.8 leading power factor is dash. So options: minus 1.2%, minus 12%, 1.2%, 4%. What is the answer? Tell me, what is the answer? Yes. A or B? How A or B? Only one option is right. Okay, enough. Enough. Okay, good enough. The answer is right. Most of you given correct. Option A is right. Minus 1.2. Minus 1.2 is correct. So for this, no calculations. No calculations. Just by observing options, we have to guess. This is possible from regulation curve only. If you know very well about the curve, you can answer this type of questions. But directly, if you don't know about regulation curve, you cannot answer this. So same type of questions you may also get again in alternatives. Okay. See, given regulation at 0.8 lagging means what? Right side. Here regulation given. How much regulation it is? How much it is? This regulation given is 12%. Now we need to find regulation at 0.8 leading power factor. Where is leading? Left side. This is our 0.8. Then if you observe, is it symmetrical curve? No. Symmetrical means then minus 12, but not symmetrical. Unsymmetrical it is. You should know that point first. Because of that, at 0.8 leading, definitely regulation is what? Negative. Negative. And small value or large value? Smaller than the 12%. See, 12% is this much. And this is only this much. Small value. So negative, small. Only one option is there. Negative, small. That is minus 1.2. Minus 12 is wrong. Positive also wrong because it is not positive at 0.8 leading mostly. Negative only will be there. So answer is A. Next, one more question. Right, one more question. A transformer has zero regulation, at if options are -1.2, -1.4, -1.8. See, don't think like this type of because they don't give this type of options first. So as a examiner, whenever any question they are creating means they will think so much. If they given this type of option, how can we answer? You cannot answer this question first. That's why they will create options accordingly. For this, you should know. Maybe now little you know about regulation curve. That's why you are feeling yes, it is very easy. Yes, easy only. But then you are creating this type of option. Suppose if you don't know anything about this question, can you create these options first? It is completely wrong. They don't give this type of options because there is no possibility to find regulation first. Okay, Vinayak. If zero also there, -1.2. Abhijit. So now I don't know why in online classes particularly people will get like so many doubts, so many doubts. Generally, we never face this type of doubts in actual physical classes. So there people will listen and they will whatever actual doubts, whatever they are getting, very, very less. But here asking doubt is very easy. So anything we can ask. But as I am reading all this, I am getting required more time to answer these doubts. So don't bring such type of doubts. Sometimes it will irritate. See, why -1.2? So while explaining, try to listen carefully because we are not concentrating anything to you, what you are doing. So at that time, you people, some of you may not listen, and after that, you will ask again how it is -1.2. Then it is becoming double, two times explanation. So clearly given at 0.8 lagging, observe 12% is given. Now at 0.8 leading, according to the figure, what is this magnitude? Is it -12? Negative only. So regulation is negative. Is it -12? No. Less than 12%. See, magnitude you verify from the diagram. Less small. 12% this much. But here less than that is there. Magnitude is less than that. Now only one option. Negative less than 12. Negative less than 12. Only one option is given. And remaining positive is given 1.24%. So only one option is possible. So that is -1.2. Okay. Right. Next, a transformer has zero regulation at 0.93 leading power factor. At 0.93 leading power factor. Then the regulation at 0.95 leading power factor is dash. Options are -2.5%, 1.2%, 12%, 14%. What is the answer? What is the answer? Yes. Okay, enough. Yes, most of you given right. The answer is 1.2 percentage. Some of you saying A -2.5. No, answer is 1.2 percentage. So this type of questions is from graph. This is from graph. Okay, some more numericals we will solve after completion of this complete topic. There you will understand actual regulation questions are not this. This is only important for objective type. In particularly competitive examinations we are getting these models. Okay, see, given zero regulation at 0.93 leading power factor having. Now what is the regulation at 0.95 lead? Just a little increases. Now you need to go to phasor regulation curve again. Observe here. Observe, regulation of transformer is zero. Where it is zero? At what power factor regulation is zero? Here. What is that power factor given? 0.93. Okay, zero point 0.9 it is, 0.93 it is. Now where where I given the question at 0.95 leading, what is the regulation? 0.95 means, now to this zero regulation, left side or right side? 0.95. Power factor is increasing in this direction, 0.0, 0.2, 0.4, 0.6, 0.8, 0.93, 0.95. So 0.95 is here. Now at this point, what is the regulation? Positive. Small positive value. See, zero regulation here, zero regulation. Now 0.93 it is. Now we are asking at 0.95. 95 is here, right side. Then it is a small positive value. Small positive. But from the given option, small positive is only option B given. Not so much increases suddenly, 12%, 14%. Little increases, positive little. That is 1.2%. Okay. What is the reason for unsymmetrical curve? So try to understand the other people. What is the reason for unsymmetrical curve? Okay. I given already why it is unsymmetrical. Based on the values we are getting, we are drawing the graph. So you are getting unsymmetrical. That's it. There is no other reason why it is unsymmetrical. Okay. Next, we need to find the condition for this zero regulation and condition for maximum regulation. Okay, let's see that. Let's say heading. Condition for maximum regulation. Condition for maximum regulation. Tell me, maximum regulation we are getting for which power factors? Lag, lead, UPF. Lagging. Maximum regulation we are getting for lagging side only. And where we are getting zero regulation? Leading power factors only. In leading power factors only, zero possible. And lagging power factor always positive, and maximum also we are getting in positive regulate. Lagging power factor we are getting. Maximum regulation we are getting for lagging power factor loads. Right. Condition for maximum regulation. Right, one point. It is possible for lagging power factor loads. Okay, it is possible for lagging power factor loads. Based on the figure we are writing, based on this curve, where you have maximum lagging side. So maximum regulation you will get for lagging. Zero regulation you will get for leading power factors. Okay, it is possible for lagging power factor loads. Now, what is the equation for lagging power factor? Percentage regulation equal to percentage or cos phi. So that equation I'm writing first. What is the equation of regulation? Percentage or cos phi plus, because lagging it is percentage x sin phi. Okay, percentage or cos phi plus percentage x sin phi. Now apply condition for maximum. How to find condition for maximum value for any function? Differentiate that function with variable and equating to 0. Same procedure here. Therefore, for maximum regulation, differentiate regulation with variable. What is variable in the equation? In this equation, variable is what? R and X, they never change. Only power factor is changing. Lagging side, you have 0.8, 0.9, 0.6, 0.5, 0.4, any power factor, variable that is. So with respect to angle, okay, with respect to power factor angle, we need to differentiate. With respect to power factor angle and equating to 0. Okay, applying condition for maximum value, then differentiate this, what we get? Percentage or cos phi will become minus sin phi plus percentage x sin phi will become cos phi. This is equated to 0. Differentiation and equating to 0. That's it. Now from here we get one condition. See, I'm transferring this minus sin phi to right side and it will become plus. So finally percentage x cos phi is equal to percentage r sin phi. If you cross multiply and if you take tan phi, sin phi by cos phi, tan phi equals to percentage x by percentage r. Then what is phi from here? Tan inverse x by r. So both numerator denominator in percentages. So I'm taking directly x by r. Phi equal to tan inverse x by r. Phi is what? Phi means power factor angle it is. See, cos phi is power factor. Phi means power factor angle. Now this power factor angle depends on what always? Power factor angle. As load is lagging power factor, lagging means RL loads. Then what is the load impedance? R plus JXL. Load resistance, load reactance, RL load. No. Then how to find the impedance angle or power factor angle from given load? How to find? So I'm writing in next page. See, so we got the equation is phi equal to tan inverse x by r. What is x and r here? Okay, don't confuse x, r, xl, rl, all this. See, this is from regulation equation, percentage r resistance and reactance. This is resistance and reactance of transformer windings. Okay, and RL XL is what? Load resistance, load reactance, because load is RL load. Now from this load impedance RL plus JXL, what is this? Is load resistance, impedance triangle I'm drawing, inductive reactance. This is impedance ZL, and this angle is the power factor angle. Okay, from the load impedance. Now what is cos phi from this, or what is tan phi? Apply tan phi to this triangle. Tan phi equal to XL by RL. Then what is phi? Tan inverse XL by RL. Load reactance, load resistance. And this X by R is our transformer winding reactance resistance. Okay. Now actual phi is this. And we got this relation by condition. Now substituting phi equal to here. Therefore, phi means tan inverse XL by RL. This is equal to tan inverse X by R. Now both sides tan inverse cancel, and finally the condition is XL by RL equal to X by R. X by R. Now what is the condition? So these conditions you may also get directly in examination. Condition for maximum regulation. X by R ratio of load. So this is we call X by R ratio of load, it is load reactance, load resistance. And what is this X by R? Transformer winding. So we call simply X by R ratio of transformer. So this is the condition for maximum regulation. What is the condition for maximum? X by R ratio of load is equal to X by R ratio of transformer. Condition for maximum regulation. Okay. So write in statement, that is X by R ratio of load is equal to X by R ratio of transformer. X by R ratio of transformer. This is condition for maximum regulation. Now what is the maximum value? How much regulation? Important this point. Maximum regulation is how much? That we need to calculate. So this condition we will substitute in the equation so that we get maximum value of regulation. Okay, completed this. Yes, X means leakage reactance of transformer. Completed. Therefore, maximum regulation of transformer is maximum regulation of transformer. Regulation maximum we need to calculate. What is the equation first? I will write that equation. Percentage or cos phi plus percentage x sin phi. Okay. Now x by r of load, x by r of transformer, both same. Means if you draw the impedance triangle for transformer winding and impedance for triangle for load, what is the load resistance? RL, load reactance XL, and this is ZL. This is load power factor angle. And transformer impedance, total transformer winding having impedance R plus JX. So if you draw that impedance triangle R, this is X, this is Z, and this angle we call generally impedance angle of transformer. If it is alternator, we call it is impedance angle of alternator. Both are same. Impedance angle of alternator there, and here in transformer, impedance angle of transformer. X by R of both are same, no? X by R of load equal to X by R of transformer. Both ratios same means phi equal to theta or not. X by R of load, X by R of transformer, both same. Means this angle is also same, phi equal to theta. Okay. So in place of phi, you can write theta also. Now percentage R. What is cos phi actually? Cos phi. From the figure, tell me what is cos phi? RL by ZL. What is sin phi? XL by ZL. Sin phi is XL by ZL. Now in place of that cos phi RL by ZL, can I write transformer R by X, R by Z, R by Z, transformer R by Z? Can I write or not? Actual cos phi means RL by ZL, but I am not writing RL by ZL. I am writing in place of that R by Z because both are same. Power load impedance, transformer impedance having same values. So anything you can substitute because we got condition is that X by R of load equal to X by R of transformer. So anything you can write. That's why I'm writing R by Z, and both I am multiplying with percentages plus percentage X as it is in place of sin phi. What is sin phi from load impedance? XL by ZL. XL by ZL. In place of that, I am writing X by Z. Transformer X, transformer Z. I am writing because phi equal to theta. Anything you can write. Or still, if you have confused, you write one more equation. Percentage or cos theta plus percentage X sin theta. Why in place of phi I written theta? Because both are same. That's why. Now cos theta is what? R by Z. Cos theta from this triangle. R by Z. And what is sin theta from this triangle? X by Z. So that is I written. Multiplying both percentages. Multiply and divide. Therefore, overall it is percentage R square plus percentage X square divided by percentage Z. Okay. Now what is r square plus x square? See, from the impedance triangle from here, what is z? Sum of these two, now vector addition, root r square plus x square. Okay, z means r square, root of r square plus x square. Now here we have only r square plus x square. So in place of that r square plus x square, can we write percentage z square divided by percentage z? Can we write z equal to root r square plus x square? Z square is what? R square plus x square. So in place of that r square plus x square, I written percentage z square. Now 1 percentage z gets cancelled. Finally, percentage z. Therefore, the maximum regulation of transformer is the percentage impedance of transformer. The maximum regulation of transformer is percentage impedance of transformer itself. Okay. Clear all of you this? What is the maximum regulation of a transformer now? The impedance of transformer only. The impedance of transformer itself, the maximum regulation. Clear? Impedance of transformer, not impedance of load. Whatever impedance of transformer is there, that is itself maximum regulation. Next, condition for zero regulation. Similarly, let's prove what is the condition where we get maximum regulation. See that. Zero regulation. Condition for zero regulation. So reading. Completed all of you this. Next, condition for zero regulation. Condition for zero regulation. Now, where we get zero regulation? For which power factors zero regulation we are getting? Yes, leading power factor. Right. Write that point. Write that point. It is possible for leading power factors. It is possible for leading power factor loads. Okay, leading power factor means RC loads. Now, what is the equation for regulation? Leading power factor, percentage regulation equal to percentage or cos phi minus. So take minus in the equation. That is for leading power factor. Percentage x sin phi. Okay, this is for leading power factor equation. Now, how to prove condition for zero regulation? How to prove? Just equate the value to zero. Just equate regulation to zero. That's it. We get one condition from here. Condition for zero regulation. So if you equate to zero, then we have percentage or cos phi equals to percentage x sin phi. Then from this, tan phi equal to what is tan phi? Percentage r by percentage x you will get. Reverse. Reciprocal of previous condition you will get here. R by x you are getting. Previously what we got x by r, but now r by x. So I'm taking it is as r by x simply. Both percentages I'm taking simply r by x. Okay. Now what is phi from this? Phi equal to tan inverse r by x. But actual phi depends on what? Load. Power factor angle depends on load again. What is the load? Leading. Then what is the load impedance? RC combination, R plus JXC. Okay, RC combination, R resistive load resistance capacitive reactance, capacitive load. Then what is the phi from that? Same, tan inverse xc by r. Therefore actual phi is tan inverse capacitive reactance by load resistance equals to, we got tan inverse r by x. Now equating both, phi I taken from load impedance, tan inverse xc by r, and it is as usual written tan inverse r by x. Now tan inverse cancel, and finally condition is what? X by r ratio of load it is equals to r by x ratio of transformer. Reciprocal. For maximum regulation both are same, x by r equal to x by r only, but for zero regulation you will get reciprocal of x by r. Reciprocal means reverse, previously x by r, now r by x, right? Therefore next page, next page. Completed. Therefore x by r ratio of load is equals to 1 by x by r, 1 by x by r ratio of transform. So this is we call, you can write r by x also, r by x ratio of transform, because x by r ratio we call generally. Then how can we consider this is reciprocal of x by r? R by x means reciprocal of x by r. Okay, this is condition for zero regulation. So these statements directly you will get in options. Write that statement. Therefore, for zero regulation, the x by r ratio of transform, x by r ratio of load, x by r ratio of load should be equals to, should be equal to reciprocal of, reciprocal of x by r ratio of transformer, x by r ratio of transformer. Okay, what is condition for maximum? X by r ratio of load is equal to x by r ratio of transformer, but it is reciprocal, or you can call r by x ratio of transformer directly. Clear? Completed all of you? Condition for zero regulation, condition for maximum regulation. What is the maximum value? Percentage Z of transformer itself. Okay, so let's see some numericals on regulation topic. See the question. The voltage regulation of a transformer having 2% resistance. So percentage R given 2%, percentage X given 5% at full load. 0.8 power factor lagging. The voltage regulation we need to find at 0.8 lagging power factor. So for 0.8 or lagging power factor, what is the equation? The percentage regulation for lagging is percentage R cos phi plus percentage x sine phi. So write that equation. Lagging they given, so take plus. Now percentage are directly there, x directly there. So substitute, direct calculation it is. Percentage r is 2, power factor 0.8. Percentage x is 5. What is sine phi? Cos phi equal to 0.8 means sine phi will be, if you don't know, root of 1 minus cos square phi. Substitute, that is 0.6 you get. Okay, 0.6. So this is 1.6 and this is 3. Total 4.6 percentage. Positive 4.6 percentage. Directly you can strike out two options here. See, option B, option C, you can strike out, and either A or D, out of these two, one will be the answer. So if you don't have in any competitive examination time to solve, and at the last minute if you want to put this question, this option, 50-50 chance now at that time. If you know that minus is not correct, because lagging case you never get negative regulation. Negative regulation is for only leading power factor. So out of A or D only the answer. So any one you can put 50-50 chance if there is no negative marking. Otherwise, if there is a negative marking, take care. Okay. So other than full load, I will tell you now how to find regulation. Okay. See, here they given at full load condition. Suppose they given at half full load, how to find regulation. So make a note of this. Note. So whatever we have calculated equation of regulations, that is for full load. So directly, but 99% they will ask full load conditions only always. But if they ask other than full load, or how to find regulation, same equation, just little multiplication is there, right here. Regulation, the regulation at any fraction of load, at any fraction of full load, at any fraction of full load is percentage regulation equals to, same equation you just multiply with x. So already we know very well about x. What is x? X is what? Fraction of full load. Suppose 50%, take x is 1 by 2 and write the same equation. Percentage or cos phi plus or minus percentage x sin phi. Okay, remember this formula for any fraction. If they say at 90% x is 0.9 or 70% x is 0.7 and so on. Okay. Next question. Next question. See this question. The percentage resistance and reactance of a transformer. Percentage are 2%, percentage reactance 4%. The approximate regulation on full load at 0.8 lagging is dash. At 0.8 lagging, what is the regulation? Same formula, previous one. Lagging is percentage or cos phi plus percentage x sin phi. Substitute here. Percentage or 2 at 0.8 plus percentage x 4.6. This is 1.6, 2.4, nothing but 4%. Okay. So mostly in these examinations, either GATE or particularly engineering services and competitive examinations, you will get the questions directly on formula based. Only in GATE, they may give some twist in the regulation problems. Okay. Next question. Next question. Direct. What is the answer? A transformer may have negative voltage regulation if the load power factor is, when we get negative, where we get leading power factors. So leading for some values of power factor. Okay, not for all power factors. In the leading we have positive, 0, negative. For some region negative we get, and for some region positive, and at one power factor 0 we get. Okay, next question. Taken. Next question. In a transformer, 0 regulation is possible at which power factor? 0 also possible for leading power factors. Remember, only for leading power factors, we have three types of regulation. 0 regulation is there, positive regulation is there, negative regulation is there. But out of these three, which is the more range for most of the power factors? Which regulation you will get? Negative regulation. Most region is negative only. Observe the diagram, regulation curve. Observe there. Positive is very small region. Small region positive, 0.9 to 1. In between there, some positive will get. But mostly it is negative only. Okay. Next question. Now try to answer this question. A transformer has percentage resistance 2%, percentage reactance 4%. What are the regulations at 0.8 lagging, 0.8 leading respectively? What are the regulations at 0.8 lag, 0.8 lead respectively? See, by observing these options, uh, one option we can eliminate completely. Which option that is? One we can eliminate. Definitely it is not correct. Which one is? C. Strike out this. Because at 0.8 lagging, if it is 1.6, at 0.8 leading, definitely it is less negative. Definitely negative, but less than 1.6. Less than 1.6. Not more than that 1.6. Because if you know the concept of that regulation curve, you can strike out this. Like that, in this type of examination, they will give options. Here only one option is there. Maybe in some questions you will get two options or three options. Then only one option, you no need to solve also, directly you can put. Okay, here you can strike out C, and remaining there is a chance. Okay, so let's calculate 0.8 lagging, 0.8 leading. First at 0.8 lagged. What is the formula for lagging? Percentage regulation equal to percentage or cos phi plus percentage x sin phi. Substitute here. 2 into 0.8 plus 4 into 0.6. So this is 1.6 plus 2.4, 4%. So if you get the 4% enough, answer is directly option A. No need to find other also, because 4 is only one option is there, lagging, and other is 4.8 and 3.8. So directly it is. And for leading power factor, if you want to find 0.8 lead, percentage equation is what? Regulation is percentage or cos phi minus percentage x sin phi. Now percentage are 2.8 minus 4 into 0.6. So this is 1.6 minus 2.4 minus 0.8 percentage. Okay. Leading power factor is minus 0.8 percentage. Yes, right. Next. Next question. Completed all of you? Read the question. Read the question. A 10 kVA 400 by 200 volt single phase transformer with percentage resistance 3% and reactance 6%, supplying a current of 50 amps to a resistive load. Okay, the value of load voltage is dash. So given voltages are what? E1 by E2. Always given rating is E1 by E2 only. What is that? 400 by 200. Okay, now we need to find load voltage. Load voltage indicates V2, terminal voltage. This V2 we need to calculate. E2 is there, 200. E2 is 200. Now what is V2? Terminal voltage. Terminal voltage. Simple. What is the load it is connected? UPF load or load, no, resistive load. For UPF load, what is the equation? Percentage regulation. We have, what is that equation? Only percentage. For UPF, the percentage regulation is percentage R itself. No need to take X here. So what is the percentage of? 3%. Or if you write in per unit, what is the regulation? E2 definition minus V2 by E2 equal to per unit resistance is 3% means 0.03. Okay. Now you have the value of E2 here. E2 is there, 200 volts. Minus V2 we need to calculate. Divided by 200 equal to 0.03. Now solve this. 200 minus V2 equal to 6. Then V2 equal to 200 minus 6, 194 volts. Okay. The load voltage is 194 volts. So if it is given lagging, then you have to take complete percentage or cos phi plus percentage x sin phi, whatever the power factor they give. Same procedure for any type of load. Clear? Yes, right. Next question. Completed all of you? Next question. See this question. So this is important model. For GATE, you may expect this type of questions. This question related to both efficiency and voltage regulation. Both. It related to both efficiency, voltage. One question is covering both. See first. The maximum efficiency of a single phase 1100 volt by 400 volt 500 kVA transformer is 98%. Maximum efficiency is 98%, and it is occurs at 80% full load UPF. So they given maximum efficiency we are getting at full load and 80% full load UPF, unity power factor. We are getting at 80%. Okay. The percentage impedance given is 4.5%. Percentage Z given 4.5%. Okay, but Rx they did not given in this. Actually, in previous questions, they are giving percentage or percentage X, and very easily you are calculating. But in this question, they did not given R and X, given only Z, percentage Z. Now you need to find R and X first. For that, they given maximum efficiency data. Okay. If you find anyone, suppose percentage R you calculated now, percentage X you will get, because once you know R, then what is X? Root of Z square minus R square. So anyone you have to find, or you can find easily from maximum efficiency condition. Simple. See, the maximum efficiency is 98%, and it is occurring at 80% full load. Means what is the value of X given? 0.8. 80% full load unity power factor. Now according to efficiency, I'm writing what is the formula for efficiency? X volt ampere cos phi divided by X volt ampere cos phi plus iron loss plus X square copper loss. So same I am writing. What is X here? 80%. So X is 0.8 into volt ampere given in the question 500 into 10 cube into UPF 1. So directly I'm writing X volt ampere cos phi divided by same X volt ampere cos phi 5 into 10 power 5 plus iron loss plus copper loss. But I don't know iron loss, copper loss also. But at maximum efficiency condition, total loss is 2 Wi or not? Tell me. At maximum efficiency condition, total loss of transformer double the iron loss, 2 Wi. That's why 2 Wi written. This is equal to 0.98. So calculate from this what is iron loss. Find iron loss from this. Tell me what is iron loss. Yes, 4081 watts. Right. Yes, 4081 watts. This is iron loss. Now, this is itself equal to copper loss or not? Yes, because at maximum efficiency, copper loss equals to iron loss. So this is copper loss, which is equals to iron loss. But at which condition this is the copper loss? This is at 80% full load. This is at 80% full load, not at full load. 80% only means we have the copper loss of 4081 watts. At which condition? At X equal to 0.8, 80%. But we can find percentage R. What is the formula for percentage R? Previously given percentage R nothing but percentage copper loss, which is full load copper loss divided by volt ampere rating into 100. Okay, so did you remember this? Now we need full load copper loss, but we have the copper loss at 80%. According to maximum efficiency is 80%, so the copper loss also at 80%. Now calculate the copper loss at full load, means X equal to 1. Full load means X is 1. Therefore, copper loss at full load equals to 4081 into 1 square by 0.8 square. Calculate this full load copper loss. How much? Calculation 6376. Yes, 6376. Right. 6376 watts. This is the full load copper loss. Now substitute in the percentage R, you will get percentage R value. Therefore, percentage R equal to percentage R equal to 6376 by volt ampere rating 500 into 10 cube into 100. Then you will get percentage. What is the percentage R now? Tell me. Percentage R. 1.27, right? 1.27. Therefore, percentage R we have. Percentage Z given in the question. Then can you find percentage X or not? Yes. Now easy it is. Now same whatever you know the procedure you can do. Okay. Percentage X calculate. Next page. Next page. Percentage X. Percentage X equal to square root. We know percentage Z square minus percentage R square. This is percentage Z square 4.5% square minus 1.27 square. Calculate what is percentage X. Yes, 4.31, right? Enough. 4.31 percentage. This is percentage X value. Okay. Percentage R is 1.27. Percentage X is 4.31. Okay. Now we have R and X terms. Now what is the first question? Read. First question. Determine the load power factor at which the secondary terminal voltage is minimum. What it means? Minimum secondary voltage, terminal voltage means regulation is maximum or zero. Regulation is maximum or zero. You are getting secondary terminal voltage minimum, very less. Means voltage drop is more or regulation is maximum. So this question related to maximum regulation. Okay. Right there if you have confusion. Minimum secondary terminal voltage. Minimum secondary terminal voltage means the regulation is maximum. The regulation is maximum. So what we have to find? Find the load power factor at which regulation is maximum. That is the question. Find the load power factor at which regulation is maximum. How to find? Simple. The first question. First question. Regulation is maximum. What is the condition for maximum regulation? X by R ratio of load should be equal to X by R ratio of transformer. Transformer X, whatever we calculated now, they are transformer reactance and resistance. Now you have that values, no? So X by R of load equal to, calculate X by R of transformer is 4.31, 1.27. Calculate this. Calculate this. Yes, how much it is? 4.31 by 1.27. Okay, right. We are getting 3.39, right? This is X by R ratio of load. Now we need power factor. Power factor is required. Directly also you can do, if you have idea of this, cos phi equal to R by Z, you can do this 1.27 by 4.5. Whatever you get, that is the answer. But I am proceeding with condition here. So equating this. So do this procedure. X by R of load is 3.39. And what is the load power factor angle? So right here clearly, load power factor angle is phi equal to tan inverse XL by RL. So this is tan inverse 3.39. Condition we equated. Then what is tan inverse 3.39? 73.6. Check it is. All of you got the same 73.6. This is phi, power factor angle. Therefore, load power factor equals to cos phi. Cos of 73.6. How much? Cos of 73.6. How much it is? Point. Yes, 28. 0.286 lagging you should mention, because lagging only we get maximum regulation. Okay. Yes, right. 0.28 lagging. Okay, 0.28 lag. So the first option, which is the first one, 0.28. So we have 0.286 lagging. Option C is correct. This is first question. 0.286 lagging. Next, second question. What is the second question? Find the voltage relating to above. So he said minimum voltage now. Now he is asking what is the voltage relating to above case. Means what is the minimum voltage? V2 how much? For maximum regulation, what is the V2? V2 terminal voltage we need to find as the regulation is when the regulation is maximum. Calculate that. Yes, right. Terminal voltage is good. 382, correct. Yes, percentage Z itself for maximum voltage regulation. Again observe रेगुलेशन क्या है E2 minus V2 by E2 है ना secondary terminal voltage is minimum observe here so whenever secondary terminal voltage is minimum difference क्या आएगा maximum आएगा नहीं आएगा yes that is called maximum regulation that's why secondary terminal voltage minimum is that is maximum regulation I said clear next second question for second question we need to find terminal voltage when regulation is maximum when regulation is maximum because above case means maximum regulation only given in the first question therefore what is the maximum regulation first regulation maximum how much percentage Z itself okay now what is the equation for regulation E2 minus V2 by E2 same for any load same equation what is the percentage Z 4.5 so in per unit 0.045 okay now E2 is there in the question what is E2 this is E1 by E2 E2 is 400 volts okay E2 is 400 so 400 minus V2 divided by 400 equal to 0.045 solve this and find V2 value how much V2 UPF what is UPF Sirisha okay right answer is V2 is what terminal voltage 382 this is the minimum voltage then regulation is maximum okay understand this question okay next question see this question see this a single phase transformer has percentage resistance and leakage reactance percentage R 1% percentage X 5% okay if the applied voltage to the transformer is 600 volts the terminal voltage at full load 0.8 lagging power factor is observed to be 230 volts see applied voltage means V1 is 600 okay the terminal voltage at full load means V2 given how much 230 okay at 0.8 lagging power factor it is we need to calculate turns ratio of transformer what we have to find turns ratio means n1 by n2 this is we need to calculate see n1 by n2 means what is exactly in terms of voltages e1 by e2 only now okay because e2 by e1 equal to previously we written in emf equation n2 by n1 or Reverse also you can take E1 by E2 equal to N1 by N2. N1 by N2 we call turns ratio. N2 by N1 we call transformation ratio. Okay. So if you want to find turns ratio, you need to calculate E1 by E2. But what they given, not E1, E2, they given V1, V2. But anyhow, for some of the numericals, if you find now approximately V1 by V2, you will get the answer. Try to find this. What is approximately V1 600 by 230? How much? Check it is how much? 600 by 230. Yes, 2.6 approximately. So near answer is what? 2.5 here. Yes, 2.5. So answer is 2.5 for this. Okay. The answer for this is 2.5. But if it is required to find exactly, then E1 by E2 only the procedure. How to find that E1 by E2? Yes, you can find. See, here I will give one important observation to you. Observe how to find that E1, E2. Observe this. Considering complete transformer circuit referred to secondary side. See, this is the primary. Primary side, I'm not taking any resistance, any reactance. Means voltage drop is what? No voltage drop. So what is the supply voltage? They said 600. Secondary side completely I referred the resistance and reactance. Observe. What is this circuit? Transformer parameters completely refer to secondary side it is. See, V1 is given 600. Then here E1 we have. Tell what is the value of E1 now? E1. Same 600 or not? Yes. E1 also 600 volts. Why? No drop. Why no drop? I transferred completely the resistance reactance to secondary. So no voltage drop on primary. E1 also 600. Okay. Now this is E2. This is V2. And total resistance, total reactance, and current I2. What they given? If they apply a supply voltage of 600, the secondary terminal voltage is observed at 0.8 lagging power factor is 230 volts. V2 they given. So we need to calculate E2. How to find? Apply the regulation formula. Percentage regulation equal to percentage or cos phi as it is lagging given plus percentage x sin phi. Same formula. Now calculate regulation first. Percentage or 1, power factor 0.8 plus percentage x is 5, sin phi 0.6. So this is 0.8 and 3.8 percentage. Okay. So regulation magnitude we got. Now we need to find E2 now. So write regulation equation is what? Next page. Next page. Therefore, regulation is E2 minus V2 by E2. This is 3.8% or 0.038 in per unit. Okay. 3.8%, but we are writing in per unit now it is. So 0.038 now. Now E2 we need to calculate. E2 minus V2 they given. How much terminal voltage? 230. This is 0.038 into E2. Now solve this equation. Tell me finally E2 how much? E2 how much? Yes, 239. Good. 239. E2 is 239. Now you have E1 already. What is E1? 600 only. E1 we have 600. And E2 is all now calculated. Therefore, turns ratio N1 by N2 is E1 by E2. This is 600 by 239. Now calculate, you will get exactly 600 by 239, 2.51. Okay, 2.51. Now you people will get doubt. Sir, I don't do this much. I will do only V1 by V2. So I got 2.6. So nearly 2.5 is the answer. I will put 2.5. But don't follow like this. Maybe here they given options. So okay, no problem. But if they given options like 2.5, 2.6, 2.7, 2.8, then what you will do? Or 2.4, one more option in place of 2.8 or 2.7, something like this, they given options. Then what you will do? Then you should not do V1 by V2. You have to find E1 by E2 only. This is the procedure to find E1 by E2. Clear? Clear, all of you? All of you clear the questions of this regulation? Okay. So one more question we solve after break. So you try to do this your own. So after break we see. Okay. So with this we complete regulation after this question. Then after break we will start the operation of transformer with non-linearity. Okay. So once that non-linearity is complete, by today mostly if possible we complete, then from tomorrow we can start three-phase transformers. Okay. Take the break for 15 minutes. Anybody did this? Okay. Option A, 322 9.2 volts, right? So this question is almost same as the previous question. Same as it is previous question. Same as it is previous question. Now let's see how to do this once. There is a rating of transformer 2200 by 220 volt single phase transformer has the following parameters. So given HV side resistance reactance, and this is not in percentages or per units. Resistance and reactance in this question are not given in per unit or percentage, given direct ohms, ohmic values, units. Okay, R1, R2, X1, X2 values given. The transformer is made to deliver a rated current at 0.8 lagging power factor to a load connected on LV side. If the load voltage is 220, see the question. If the load voltage is 220, the terminal voltage on HV side is dash. Terminal voltage on HV side. See, try to understand this question properly. First, I am drawing figure. Transformer complete circuit refer to secondary. I am drawing again same as it is previous diagram. Total resistance R0 to X0 to, and load is connected here. Observe. This 2200 by 220 is what? E1 by E2 actually. But observe, first I will take primary side, no voltage drop because no resistance, no reactance. So V1 is how much? This is E1. Whatever E1 is there, both are same. V1, E1 both are same because no drop here because totally we transferred no secondary side R0 to X0 to. No resistance, no reactance on primary. V1 is 2200 because E1 also 2200. Both are same. If E1 is 2200, what is E2? 220 according to given data, 220 volts. Then there is a current I2. And what is the power factor of load given? 0.8 lagging. So there is some load. This is our terminal voltage. 0.8 lagging power factor load. So actually, if the supply voltage is 2200, EMF E2 secondary side 220, then what is V2? Then V2 definitely less than 220. Let us take for example 210. For example, not exactly example, just 210. 210 volts. So you are getting secondary terminal voltage less than 220. But observe the question once. If the load voltage is 220, the terminal voltage on HV side. HV side means input side. HV is what? Input. This is HV. This is LV. Terminal voltage HV, how much required? See, if V1 is 2200, what is the terminal voltage on LV side? 210, not 220. So if you want 220 here, if you want 220 here, you should increase this V1 or not? Yes, you should increase little voltage. Then how much voltage you should increase? Can we increase directly? Suppose if you are observing, you can increase by observing the load. Load is somewhere else, your transformer is somewhere else. So how to increase this voltage? How much to be increased? We need load voltage 220. For that, you should increase the supply voltage. How to increase that supply voltage? So simple. You calculate first what is the percentage regulation of transformer from the given data. Some percentage you will get. Now, what is the meaning of that regulation? This much voltage drop in transformer. Suppose you got some 3%, for example. 3% voltage drop in this. So if you want 220, if you want 220 volts at the load, you should increase the voltage. How much voltage to be increased? Whatever voltage drops, that much voltage you should add additionally to primary. Clear? whatever voltage drops in transformer, that much percentage of voltage you should add in the transformer. And one more important point is this percentage regulation will be same whether you calculate on secondary side or if you calculate on primary side. It is applicable for both the sets. The percentage regulation applicable for both sets. Whatever you calculated, that much voltage you should add. So therefore, make a note here. Note, to maintain load side voltage or load voltage, to maintain load voltage as 220 volts, 220 volts, the input voltage should increase. The input voltage should increase by percentage regulation. Should increase by percentage regulation. Whatever regulation you got, that much voltage you should add. That is V1 new voltage. So new voltage, new supply voltage equal to, already there is some V1 plus additionally whatever drop, percentage regulation into V1. So whatever voltage drops, that much voltage you should add additionally to the existing voltage. So this is the equation, remember. Okay. Same we will use again. Previous question I'm going again. Now what you will do is calculate total resistance referred to secondary, total reactance referred to secondary first. R0 to X02. Calculate this. What is R02 means? R2 plus R1 dash. And what is X02? X2 plus X1 dash. Calculate first these two. Calculate first these two. See, K equal to, what is K from the given? 2200 by 220, no? So 220 by 2200. This is K. Calculate K first. Transformation ratio 0.1. K is 0.1. Now R02, R2 plus R1 dash. R2, what is R1 dash means? K square R1. Okay. R2 is there, R1 is there. So just substitute here. What is R2? R2 0.028. 0.028 0.028 plus K square 0.1 square into R1. What is R1? 3.4. 3.4. Calculate this. Calculate this. How much? Yes, 0.062. Okay, right. 0.062. Similarly, find X02. X2 plus X1 dash. X2 plus K square X1. Substitute here. Calculate what is X02. Tell me directly. Yes, 0.132. Right. 0.132 ohms. So resistance we have, reactance we have. Therefore, per unit regulation or percentage regulation, anything. So I'm writing in per unit. How we write? If you remember, I2 R02 by E2 only now. This is R per unit or per unit resistance we call. So I'm not writing directly per unit resistance or percentage resistance. I am writing its formula here. In equation we got it yesterday. We during the derivation we got this one only. In place of that we written per unit resistance. Okay, cos phi plus I2 X02 per unit reactance it is by E2 sin phi. So substitute in this equation all this. I2 means what? Rated current given in the question. Observe. See, transformer is made to deliver rated current at 0.8 lagging on LV side. LV side rated current means how to find? You can find, now it is. Yes, ILV. Rated current on LV side. Volt ampere is 5 into 10 cube divided by 220. Calculate this. What is the rated current? Yes, 22.7 amperes. Okay. Now I2, R0 to E2, everything we have. Substitute. I2 is 22.7, R02 we got 0.062 divided by E2, 220 into cos phi, what power factor 0.8 plus I2 22.7, X2 we calculated 0.132 by E2 220 into sin phi is 0.6. Calculate this, how much regulation? How much regulation? Hmm. How much? Yes, 0.013 or 13 percentage. Not 13, 0.013 or 1.3 percentage. Okay, regulation is this much, 0.013. So this much or 1.3 percentage, 1.3%. This much voltage drops in transformer. So if you want 220 at load, you should increase some voltage. Then how much voltage to be increased? Whatever drop, that is we calculated 1.3. Therefore, new voltage to be applied equal to 2200 already applied plus whatever regulation 0.013 into 2200. This much voltage additionally we are applying. Calculate this. Calculate how much? Yes, 229 volts, right? 229 volts. So this is the new voltage we need to apply. If you apply this much voltage now, your terminal voltage now will become 220. Okay. Yes, right. Okay. What is given in the question? See one more time. There is a rating of transformer 2200 by 220. So actually, if the input side is 2200, E2 is 220, then what is the V2? Less than 220 we get. How much? For example, I taken 210, less than 220. But in the question they are asking if the load voltage is 220. Load voltage means V2 should be 220. If V2 should be 220 means when you will get 220 here, if you increase this primary or supply voltage, we need to increase. How much to be increased? How much to be increased? Whatever voltage drop taking place, that much voltage we should increase in the primary side. How to find that? That is nothing but voltage regulation. So that voltage regulation we calculated, we got 1.3 percentage. Okay, whatever regulation we got, that percentage of voltage we are adding additionally to primary side. If you add that much voltage, what is the new voltage we got? 2229 volts. Previously 2200 only, but 29 volts additionally we given. Okay, then your terminal voltage will become 220. If input voltage increase, correspondingly all voltages increases, and finally that load voltage will become 220 volts. Clear all of you this? Yes, we can apply because you are not applying very high voltage, just 29 volts you are increasing, no problem. 0.8 power factor we considered now. 0.8 we substituted observe in the formula. Okay, so with this the regulation we are completing here. Now up to this total single phase transformer is complete. So up to now we have not seen anything about three phase transformer. No, whatever we have seen, voltage regulation, efficiency, you will get again in three phase transformer. So with respect to three phase transformer, you have to solve voltage regulation if they ask, or efficiency if they ask, these type of questions. Okay, so we will see briefly in between that questions how to solve voltage regulation or efficiency in three phase transformer. Okay, before starting three phase, we should complete the operation of transformer with non-linearity of core. That is most important task. And if you understand well, it is the three phase transformer, you can understand easily. Okay. So in ideal transformer, we have the fifth ideal property. Fifth ideal property. So what are the five ideal properties? First one, permeability of core is infinite. Second, iron loss is zero. Third, resistance of winding is zero. Fourth, leakage flux is zero. And fifth, shape of BH curve is linear. But practically is all possible? No, we have taken first four and fifth we left, and that fifth point we are seeing now. Okay, so right side heading, operation of transformer. Operation of transformer with non-linearity of core. With non-linearity of core. Okay, operation of transformer with a non-linearity of core. Why non-linearity? See, whatever the core material, ferromagnetic materials we are using, due to that ferromagnetic materials, what is the shape of that BH curve? Previously we have seen in iron loss also, non-linear hysteresis curve we call, or BH loop we call. So every ferromagnetic materials will have that BH loop or BH curve or magnetization curve also we call this one. So the shape is non-linear, but ideal case what it is? Linear. When it is linear, what is the shape of current and flux? When it is non-linear, that is mainly due to BH curve, what is the shape of current and flux? So little concentration required from your side. So here we cannot force anything, we cannot say anything, who is watching or who is not watching, who is listening and who is sleeping. So we cannot see anything. That is completely your command only. So our command is nothing here. So you concentrate well if you want to get clearly the idea of this non-linearity. Concentration important. And in between, if you sleep or if you are going for somewhere, don't ask in between how it is again. So I will give the first time itself clear data, and again after some time again some people will ask, so how it is? Yes, that is not my problem again, because already time is less. Around 15 days we are taking transformer, like the total machines 2 months it may take. So concentrate as much as possible. First I will take ideal case only, then I will show you what is with ideal case, and now what is practical case problem. Okay, right. First, ideal transformer. Ideal transformer. Ideal. So ideal case, what is the shape of BH curve? Linear. Linear BH. The shape of BH curve in ideal case is linear, like this. Means B proportional to flux always. B means field axis or flux axis. H means current axis. So you have to consider every time B is flux and H means current axis. Now, whenever current increase, what is the flux also increases linearly. So this is linear. Whenever current increase, flux also increases. So both increase simultaneously. When flux increase, current increase. And when current is maximum, flux also maximum reaches simultaneously, both linear case. So due to this linear BH curve, what is the shape of current and flux? What is the shape of current flowing from the source always? What is our source always? Sinusoidal. Whatever input we are giving to transformer, that is source, is always sinusoidal source only. Do you have any other source? We have other source, but what we are generating from generators. Who will give supply to transformer? Generator. From the generator, we are giving supply to transformer. What is the output of generator? Purely sinusoidal. So the current is sinusoidal. The shape of current is sinusoidal. This is current. And which current is responsible to create flux in the core? To create flux, what is the current we taken in the initial classes? Magnetizing current, I mu. I mu producing flux in the core. So let it is I mu, magnetizing current. This is magnetizing current, I mu. Okay. Now, whenever current increase, flux increase. So the flux also same as it is current shape sinusoidal. Both are in phase. Current and flux both are in phase. Okay, magnitude is different, current is different, flux is different, but anyhow both are sinusoidal only. Okay, current is sinusoidal, so flux also sinusoidal. Whenever flux is sine, what is the EMF induced in the winding? That is also sinusoidal. Okay, EMF induced in the winding is also sinusoidal. No changes. Current supply current sinusoidal, flux produced sinusoidal, EMF induced sinusoidal. This is ideal case. But practically the shapes after this you will see little changes. Okay, but ultimately what we required from transformer, whatever EMF induced in winding, that voltage should be what? Sine. Whatever you are taking from transformer, we are taking voltage, and that voltage from transformer should be sinusoidal. Otherwise, if the voltage is not purely sinusoidal, if it is having any harmonics, then what happens to our load? So that I will show you what is the problem with harmonics there. Okay, write one point here. Write one point. Second figure. Right. In ideal case, to produce sinusoidal EMF, to produce sinusoidal EMF in the windings, in the windings, the shape of flux in the core is sinusoidal. The shape of flux in the core is sinusoidal. The shape of flux in the core is sinusoidal, and the shape of corresponding current and the shape of corresponding current is also sinusoidal. Ideal case all same only, sinusoidal only, everything, current, flux, voltage induced, everything sinusoidal. But practically it will change due to non-linearity of core. Okay, let's see that practical case now. This is ideal case. Next, practical transformer. Saturday. Practical transformer. Practical transformer. Now, practical transformer, what is the shape of that BH curve? Particularly due to hysteresis, we have seen in iron loss. What is the shape of that BH curve? Non-linear. So I'm drawing that. The shape of BH curve is non-linear like this. So don't draw completely, draw after completion it is. The BH loop is little thinner for ferromagnetic materials. So I'm drawing the same. Okay. This is our BH loop, also called hysteresis loop. Okay, observe carefully. This is magnetization process. H proportional to current, D proportional to flux. Okay, and this is demagnetization process. Now with respect to this, I'm drawing the shape of current and flux. Okay, observe carefully now. Tell me first, in transformer, ultimately what we require, the EMF induced in winding must be sinusoidal. Okay, because that EMF only we are taking to our loads. So our load will work properly when the EMF or voltage from transformer is sinusoidal. For that, we need always EMF in winding sinusoidal. When EMF induced in the winding is sinusoidal, EMF is due to flux in the core always. So EMF is completely depends on flux. So if the shape of flux in the core is sinusoidal, the EMF induced in windings also sinusoidal. So for that reason, I am considering the flux in the core must be sine wave. Okay, so I'm considering directly the flux must be sinusoidal. Okay? The flux in the core must be sinusoidal. So I'm considering this. This is flux. So this is flux in the core must be sinusoidal because the EMF required for me completely sinusoidal. It is sinusoidal only when flux is sinusoidal. That's why I taken flux in the core must be sin. Now check, in order to produce sinusoidal flux, previously what is the current in the winding we taken sinusoidal because ideal case that is. But practically due to this non-linearity, the shape of current will change now. See how it will change. Observe this from here. Previously, in ideal case, one important point. See, whenever current is zero, what is the flux also? Zero. Okay, current zero, flux also zero. Now, when current increase, what is the flux also? Yes, linearly increase. Now, when current maximum, what is the flux also? Maximum reaches. That is ideal case, linear case. Now, let us apply same as it is for non-linear case. See this. Now, due to this non-linearity, observe here. See, here what is the current? This is current axis. H means current axis. There is some current here, but what is the flux? Zero. Whenever or see, whenever there is a current I, some positive value, here current is positive, and what is current here? Negative. This is current minus I. This is minus 5 flux. When current is positive, flux is zero, or when current is negative, flux is zero. Or observe here along the field axis or flux axis, there is some flux here, but what is the current? Zero. Whenever current is zero, flux is there positive, or flux is there negative, or whenever flux is zero, current is there positive, current is there negative. So whenever current is zero, flux is not zero at that time. There is some small amount of flux, positive amount, and one more time negative flux. One time positive, one time negative. This is okay. Current zero here, but there is a flux. That is due to residual flux. We have seen already that concept is cleared over. Now only we are considering current flux variation here. Similarly, whenever flux is zero, what is the current? Is it zero? No. There is some small positive current and negative current in other half cycle. Okay. So current zero, flux zero at a time we are not getting. But in ideal case, when current is zero, flux also zero. But in non-linear case, current 0 point, flux 0 point is not taking place at a time. Okay. Now, this is observed. See, current increases, flux also increases. Current increase, flux also increase. And current is maximum here. Almost flux also maximum. Maximum points at a time we are getting. Whenever current is maximum, flux also almost maximum value. Okay. Okay. When current is zero, but flux is not zero. Now listen carefully. So we taken directly flux is sinusoidal because EMF required in the winding sinusoidal. No. Now observe from this. Whenever flux is zero, this is flux is zero. Flux is zero here. But what is the current? See, this is current positive, small positive current, but flux zero or not. This is flux axis zero here. Current is there, but flux is zero. So when flux is zero, there is a small amount of current. Now from now, current increases, current increases, current increases, current increases. But flux increasing or not? Yes, flux also increasing, flux also increasing. So from here, whenever current increase, flux increase. But how that variation? Observe, for small variation of current, there is a large variation of flux because ferromagnetic material, small current is enough to drive or to produce maximum or highest flux. For small current, more flux will produce because of ferromagnetic materials. Due to that, from current is there, flux is zero at that time. So whenever current increase, flux also increase. But which increase is more? Flux increment is more. So current slowly increase. Current increasing, flux also increasing. Current reaches maximum, flux also reaches maximum. So both at a time reaches maximum value. Current increase, flux also increase. Current maximum, flux also maximum. Okay. From now, see, flux is decreasing. Flux is decreasing. And here there is a small amount of flux. But what is the current? Current decreases. Whenever flux is decreasing, current also decreasing. And whenever flux reaches to this much magnitude, what is the current here? Completely zero. Okay, same thing I will apply in this waveform now. Observe. From this maximum point, whenever flux is decreasing at this particular value of flux, at this particular value of flux, the current reaches zero. So for this magnitude of flux, what is the current? Zero. So current is zero, zero. So exactly at this magnitude of flux, what is the current? Zero. Okay, current is zero here. From now, current increases in the reverse direction. And what is the flux? Decreases to. Whenever current reaches little negative value, what is the flux now? Zero. Okay, like that, whenever current is increasing in the reverse direction, at a particular value of current here, what is the flux? Zero. At a particular value of current in reverse direction or negative current, the flux is zero. Again, from now, current increases in reverse direction, flux also increases. Now same thing. So once you draw first half, other half you can draw easily. So other half will continue like this. Okay, like this you will get. So exactly I will try again, check. See, this is the variation of current. Okay, whenever current reaches again positive, flux will be zero at that time. Current zero, flux zero will not take place at a time. So that you should observe, and based on that variation, we are drawing current signal. So this is what current signal it is. Which current it is? I mu or I naught? I mu or I naught? In previous ideal case, I said that is I mu to create flux. Ideal case, that is I mu to create flux. But in practical case, BH loop we have or hysteresis loop we have means there is some loss in the core or not? Yes. Then under no load operation, what is the current drawn by transformer? Initially we call no load current. So this current is the no load current, also called exciting current IE. I naught or IE, no load current or exciting current. Now this no load current is the sum of two currents or not? What are that? Magnetizing current plus iron loss current, two currents. Now this I naught, this signal I naught, I will resolve into two components. Now I will draw two signals again. This I naught I will draw as two signals. One is I mu signal, one is IW signal. So first complete up to this. I will draw again this. Completed this one. See, to produce sinusoidal flux, the current drawn by transformer is not sinusoidal. Why it is not sinusoidal? Because of this nonlinearity. Based on this nonlinearity, we have drawn current signal. Because flux and current are not zero at a time, and current and flux reaches maximum at a time. Based on the hysteresis loop, we are drawing this current signal. But ideal case, what is the current? Sinusoidal only, but not here. Now, this I naught or IE, exciting current or no load current we call, it is resolving into two components. One is I mu, one is IW. So observe carefully how I am drawing these two signals. So here itself I am drawing. So I will resolve this current into two components. See, try to understand, because from the signals only you should understand how we got that. See, this is I naught. Now I am resolving this current into two components. One is this. So one component is this, and other component is like this. First draw, I will tell how we are drawing this. Very interesting. This is okay. This is one current signal. This is one signal. This red line, and this black one is one signal. Two signals, because I naught is sum of two currents, I mu IW. Now in this this red one is IW, iron loss current, and this black one is I mu. This black signal is I mu. What is I mu? Magnetizing current, which is the main reason for creating flux in the core, magnetizing current. And IW is what? Iron loss component of current. Now why I drawn? If you add I mu and IW, you will get I naught here. This one, same shape you will get. Check how it is. Observe. Now at this point, that is at t equal to 0, for example, or 0 degrees. At this 0 degrees, see, at this 0 degree, what is the no load current? A small value. Then observe here. In this I mu is 0, but IW is what? Maximum. IW means cosine term. I mu means sine term. That's why I drawn like this. And if you add these two signals, what is the resultant of this? This much only. Okay, that is the value of I naught. Now, from 0 to 90 degrees, 0 to 90 degrees, I mu increasing, IW decreasing. I mu increase, IW decrease. Then if you add the resultant of these two, you will get the shape like this or not? Yes, yes. So exactly at 90 degree, this IW term is 0, but I mu is maximum. I mu is maximum. So due to that, the value of I naught will be there this much. Even IW 0, there is magnitude of I mu, so this much. Now from 90 to 180 degrees, from 90 to 180 degrees, check, I mu decrease, but IW negative. That's why it is decreasing very quickly here. I mu decrease, but IW negative value. That's why it is decreasing so much. And exactly at this angle, observe this. This is having this much magnitude, and this is having negative. These two gets cancelled, and you will get the no load current exactly 0 here. This is a small positive, this is a small negative. The sum of these two will be 0. So a no load current is 0 here. Okay. Now at 180 degrees, negative current, I naught is what? Negative, because at 180 degree, I mu 0, but only IW is there, negative value. So the sum of these two signals will be no load current, I naught. So we need to concentrate mainly about here I mu, because in order to produce sinusoidal flux in the core, which current is responsible for us? Magnetizing current. So what is the shape of that magnetizing current here? See, the shape of magnetizing current is, it is not sinusoidal. What is the shape we call? Peaky wave. The shape of magnetizing current is peaky wave. So if you want to produce sinusoidal flux, what should be the shape of magnetizing current in a practical transformer? Peaky wave. Then flux is sine, EMF also sinusoidal. Okay, clear all of you up to this? We write these points now. I will tell. So while keep on going, you will understand each and everything. So don't get doubts now itself. You will understand everything once it is little proceeds. Okay. Supply is sinusoidal always, no doubt. The supply sinusoidal only. Then how current will become peaky wave? So that is also we will see now. Wait. So completed up to this first. Very difficult to follow the cursor pointer. वो तो फॉलो करना है ना ऑनलाइन क्लास के. अगर ऑफलाइन होता तो हैंड मूव होता है क्लास में, उसे ऑब्जर्व कर सकते हैं, मगर ऑनलाइन में क्या ऑब्जर्व कर सकते हैं? ओनली कर्सर. Okay, next page. First write the statement so that we will go to next. So what is this? In order to produce sinusoidal EMF, flux in core should be sinusoidal. So to produce sinusoidal flux, what should be the shape of magnetizing current? Peaky wave. If it is peaky, flux we are getting sinusoidal. Flux is sinusoidal. Okay, flux is sinusoidal. Write that point. In practical transformers, in practical transformers, to produce sinusoidal EMF, to produce sinusoidal EMF, the flux should be sinusoidal. The flux should be sinusoidal. The flux should be sinusoidal. To stop. To produce sinusoidal flux, to produce sinusoidal flux, the shape of magnetizing current in the winding, the shape of I mu, magnetizing current in the winding, should be peaky wave or should not be sinusoidal. It should not be sinusoidal. Ideal case it is sinusoidal, but practically it should not be sinusoidal. What should be the shape required? Peaky wave. Should not be sinusoidal, comma, it should be a peaky wave. It should be a peaky wave. Okay, it should be a peaky wave. Now, peaky wave. How can we supply peaky wave? Can we supply peaky wave? What is the source available with us? Sinusoidal. So you can supply a current sinusoidal. But how can we produce peaky wave current? Peaky wave we no need to produce. Peaky wave we no need to produce. We are supplying sinusoidal. We will supply sinusoidal only. Then how it will become peaky? Yes. it will become peaky automatically in single phase transformers. In three-phase transformer, we have two types of three-phase connection: delta connection, star connection. There it depends on type of connection, but single phase transformer there is no problem at all. So why there is no problem, I will show you again. So before that, first we need some Fourier series analysis to understand clearly. Right here, make a note make a note. First point, according to Fourier series analysis, according to Fourier series analysis, if a signal is non-sinusoidal, means the signal is having harmonics or not. Any signal which is non-sinusoidal, the signal will have harmonics in that. And what harmonics? We have two types of harmonics: odd harmonics and even harmonics. So first write that according to Fourier series analysis, if a signal is non-sinusoidal, but symmetrical, then it consists of then it consists of which harmonics? So I will draw the signal. For example, this is signal is non-sinusoidal. Non-sinusoidal means just like our peaky wave. Now itself we got peaky wave like this. This is peaky wave. Non-sinusoidal it is. And symmetrical. Symmetrical means what? The positive peak and negative peak having same magnitude or not? Yes. The positive half, negative half equal. So this is symmetrical. Then what are the harmonics it is having? According to Fourier series, odd harmonics. Then it consists of odd harmonics. Odd harmonics. What are the odd harmonics? 1, 3, 5, 7, 9, and so on, like this. Odd harmonics. Now in that, the first one we call, this is one means fundamental. One means fundamental always. One is called fundamental. Fundamental. What is the shape of fundamental? Sinusoidal. Suppose there is no harmonics, no, then we call that is a fundamental signal. Means purely sinusoidal it is. But there is harmonics: third harmonic, fifth harmonic, 7, 9, and so on. But out of all these harmonics, which is the most dominant harmonic? Dominant. Third harmonic is called the most dominant harmonic. After fundamental, whatever is there, that is called dominant harmonics. So third harmonic is dominant harmonic. And fifth, seventh, ninth, higher order harmonics, the effect will be negligible. So what is this? How can we draw with respect to harmonics signal? Observe. Suppose if I draw all these harmonics in one graph, it will be like this. Fundamental means purely sinusoidal. This is one. Now what is meaning of third harmonic? Third harmonic means the signal will complete 3 cycles in one fundamental cycle. That is 3 cycles here. 1, like this. 3 cycles. This is fundamental. This is third harmonic. Now fifth harmonic. What is meaning of that? It will complete 5 cycles in one fundamental. 5 cycles. So 5. So I am not counting randomly. I am drawing. Assume that this is 5. Whatever it is. This is fifth harmonic. Next 7. Seventh harmonic. Okay, seventh. Like that, if you observe, if you go to higher order, 9, 11, and so on, what is happening? Fundamental magnitude this much. Third harmonic reduced. Fifth harmonic still reduced. Seventh still reduced. So like that, if you go to higher order, the magnitude of that harmonic will reduces. And which effect is more on the fundamental signal? Third harmonic effect, because its magnitude is more, little more compared to other harmonics. So the effect of that higher order generally we neglect. We are neglecting. So which harmonic effect is important for us? Third harmonic effect is important. Okay, means if you want peaky wave signal, which must be there in the harmonics, fundamental is there plus third harmonic should be there. Fundamental is there already, and if there is a third harmonic signal, fundamental plus third harmonic signal, the shape of current will become peaky wave. The shape of current will become peaky wave. So now tell me, if you want to produce a peaky wave current, there must be third harmonic in the signal or not? Yes. If third harmonic signal is there, the current will become peaky. Suppose there is no third harmonic, zero it is. Now tell what is the shape of current? Sinusoidal, because only fundamental is there. If there is only fundamental, the shape of current is sinusoidal. So if you want peaky wave, the signal should have fundamental plus third harmonic. If both are there, the shape of current is peaky wave. Higher order we never consider. Higher order we are neglecting because the effect is very, very small on fundamental signal. So mainly third harmonic is important for us. Okay, clear all of you this one? See, fundamental plus third harmonic. So I will draw only the two, then you will get a peaky wave signal. Observe how it is. Observe this. If there is fundamental, sinusoidal, fundamental means sinusoidal always. There is a fundamental signal plus third harmonic signal. This is third harmonic. So why I started from negative half? Because see, total current I mu equal to fundamental Im1 sine omega t. How to write third harmonic in signal? Im3 magnitude sine 3 omega t. Because what is the frequency of third harmonic? 3 times. 3 cycles in one fundamental. Like that, if it is fifth harmonic, how to write? Im5 sine 5 omega t, and so on. Okay. So if you draw only fundamental plus third harmonic, we are neglecting any of fifth harmonic. Then if you add these two signals, what is the resultant shape you get? Check the resultant. See, because of third harmonic effect, see, this is 180 degrees, 360 degrees, and here you will get like this. The magnitude of fundamental will reduce, and at this 90-degree, third harmonic also having peak magnitude peak, positive peak, and this is also positive peak. So resultant current will be like this. Okay, like this peaky wave current you get. So in order to produce peaky wave, third harmonic very important for us. Okay, just keep in mind this point, third harmonic required in order to produce peaky wave current. If there is no third harmonic, what is the shape of current? Sinusoidal. Okay, this is first point in Fourier series analysis. If a signal is non-sinusoidal but symmetrical, it consists of odd harmonics. First point. Next, second point. Right, second point. Under note. Second. Second. If a signal is non-sinusoidal, non-sinusoidal, but non-sinusoidal and unsymmetrical, non-sinusoidal and unsymmetrical, then it consists of which harmonics? Tell me. It consists of which harmonics? If a signal is non-sinusoidal and but symmetrical, then it is having odd previously. But now signal is non-sinusoidal and unsymmetrical, then it consists of both odd and even harmonics. Both odd and even harmonics. Both it is having. Okay. Now what are that example? If you take let this is a unsymmetrical signal. This is unsymmetrical. Let us take non-sinusoidal, for example. This is unsymmetrical. Non-sinusoidal, unsymmetrical. Then what are the harmonics? Odd and even means 1, 2, 3, 4, 5, 6, 7, and so on. All the harmonics, odd 1, 3, 5, even 2, 4, 6, 8, and so on, means all the harmonics it is having. Now, one is called again fundamental. Then which harmonic is most dominant in this? Second harmonic is most dominant. Remember these 2 points. This point also we use in some other topic. Okay, remember this. Okay, so right, third point in the note. Third one, third point. Right. In order to produce peaky wave current, in order to produce peaky wave current, peaky wave current, there must be third harmonic signal. There must be third harmonic signal. Third harmonic signal. Otherwise, it will become sinusoidal. It will become sinusoidal. It will become sinusoidal. Now, if current is sinusoidal, what is the problem? So we have coming from EMF sinusoidal. For that we need flux sinusoidal. Then what is the shape of current we got? Peaky wave. This is okay. But if current is sine, means third harmonic is not there. If current is sinusoidal, what happens to flux signal? Then definitely flux signal will change. Then what is the shape of that flux signal? And what will be the EMF after that? What is the shape of that EMF? We need to consider. So write it, that is in fourth point. Next, fourth point. Write that. Fourth point. If shape of current, shape of I mu is sinusoidal, if shape of I mu is sinusoidal, then the shape of flux is, the shape of flux in the core, shape of flux is flat top. So how it is, I will show you. Just write first. Flat top, also called trapezoidal shape. The shape of flux is flat top or trapezoidal. So how it is flat top, I will show you with the signals. And shape of EMF is, shape of EMF in the winding is peaky wave. Shape of EMF is peaky wave. So remember, very important questions. If current is sinusoidal, what is the shape of EMF induced in practical transformer? The shape is peaky wave. And what is the shape of flux in the core is flat top or trapezoidal shape. So I will draw all the signals now. First write this statement, flat top or trapezoidal. That is, if you indicate in signals, let this is shape of current I mu. What is the shape of current? I said sinusoidal. If it is sinusoidal, what is the shape of flux? Flat top. Flat top means like this. This is the shape of flux. Shape of flux is approximately like a flat top shape. Okay, like this, flat top or trapezoidal shape we call. Then what is the shape of EMF? Peaky wave. It is like this. The shape of EMF is peaky wave, like this. Just now we have drawn a magnetizing current, peaky wave, like this we get. The shape of EMF in the winding will be peaky wave. Okay. Now let's see how we are getting these shapes. How we get these shapes, I will show you now. Okay, completed up to this. So first I written statement, that is I given in signals. Now how it is, I will show you. See, let us consider, let What is the magnetizing current? Sinusoidal. Sinusoidal means only fundamental. That is I mu equal to Im1 sin omega t. Fundamental it is. Fundamental signal like this we write Im1 sin omega t. No harmonics. So current is sinusoidal. Then what is the flux? If current is sinusoidal, flux will become non-sinusoidal. Non-sinusoidal flux means what? It is having harmonics or not? Yes. So the flux is having fundamental phi m1 sin omega t plus third harmonic phi m3 sin 3 omega t plus phi m5 sin 5 omega t. Flux is non-sinusoidal. Okay, that is flat top means non-sinusoidal. It is having odd harmonics. That is I am writing 1, 3, 5 and so on. But only fundamental third harmonic we consider. Fifth harmonic and so on we neglect because the effect of higher order is always less. So only that fundamental signal, third harmonic signal. So these two only we are considering, neglecting that fifth harmonic. Okay. Now if you draw the shape of flux with respect to fundamental and third harmonic, let fundamental means phi m1 sin omega t, sinusoidal na it is. So I'm drawing sinusoidal. Okay, this is first fundamental, it is fundamental flux phi 1 phi m1 sin omega t I drawn. Next third harmonic phi m3 sin 3 omega t. Now this is omega t time axis. Now tell me, this is sin omega t. Now what is sin 3 omega t? Signal how we get? Whenever omega t is 0, what is 3 omega t? 0. 3 omega t 0. Okay, listen carefully. 3 omega t I have to draw. This signal I have to draw now. Third harmonic signal. This is omega t 0. Third harmonic means it is completing 3 cycles in one fundamental. This is 60 degree. This is 120, 180, 240. This is 300. This is 360. Okay. I am giving proof how we get this third harmonic here. Observe. When omega t is 0, sin 3 omega t is 0. When omega t 360 degree, what is sin 3 omega t? Sin 3 omega t, 3 into 60. Or if you take here, for example, 30 degrees, 30. This is 30 degrees, 0 degree. This is 30 degree. This is 60 degree. Now what is sin? This is 30 degree. Sin 3 into omega t. Then if omega t equal to 30 degrees, what is sin 3 omega t value? Just 3 into 30, 90. Sin 91 means it is increasing like this or not? Yes. And then it will decrease. This is 3 omega t. Like that, continue the same. Continue this. Third harmonic signal. 3 cycles in one fundamental. So phi m1 sin omega t fundamental, and this is our third harmonic flux. Both I drawn. Then what is the resultant shape? We get check. Resultant of these two. How we get resultant? Verify here. Resultant. See at 90 degree, phi 1 having positive peak, but third harmonic flux having negative peak. Then what is the resultant flux? Little reduced. So from I will draw directly, approximately will get increasing and then slightly decrease at 90 degrees. Like this we get. And for negative half also same as it is. Little it will decrease. So this is the shape of final resultant flux. What is the shape we call it is approximately? Approximately it will be a trapezoidal. Like a trapezoidal shape. Actual trapezoidal is like this. Okay. Almost same you will get here. Almost same. So this is flat top or trapezoidal. Flat top shape or trapezoidal shape. Okay. Now EMF will become peaky wave, I said. How that is peaky? So first complete up to this. Draw the figures quickly. Draw the figures quickly. So if anybody missing today and by tomorrow, when we say directly this is the shape of current or flux, don't ask at that time how it is. Okay. I said already, this is important. You need your concentration only here. So if you miss again in some of the topic in the next classes, you cannot answer this. At that time, don't ask how it is, because newly people will come at that time and they will listen, and how it is they will get doubt. So they are getting doubt. That is okay, accepted. But again, how can we explain all this? That's why in the starting itself I said this fifth property is little important, little concentration, little confusion also. Not confusion, but first time maybe when you are listening, maybe it looks like little difficult. But after completion, go through that once, one more time, so that you will understand clearly all the points. Okay. Next. Next, EMF I said peaky wave. EMF is what? Peaky wave. Let's see how we are getting EMF peaky. See, according to Faraday's law, what is EMF induced always? Minus N d phi by dt. Okay. What is the flux? Just now I taken flux is this phi m1 sin omega t plus phi m3 sin 3 omega t and so on. So I am writing here minus N1 if it is primary side EMF induced d phi by dt. D by dt of phi m1 sin omega t plus phi m3 sin omega 3 omega t, because third harmonic, fifth harmonic sin 5 omega t and so on. Only these two we are considering, neglecting higher order. Now if you differentiate, you will get minus n1 d by dt of this sin omega t is what? Cos omega t. So phi m1 into cos omega t. Okay. Plus d by dt of this sin 3 omega t is what? Cos 3 omega t. Cos 3 omega t differentiation into 3 with respect to t we are doing into 3 omega. So finally phi m3 it is phi m3 into 3 omega into cos 3 omega t plus and so on. Just differentiation I applied, nothing. Now if you write in terms of complete equation, it will come like some minus em1. So overall I'm writing magnitude. This is magnitude, no, whatever is there here, magnitude it is em1 cos omega t minus remaining total I'm writing as em3, total whatever is there here, em3 cos 3 omega t minus and so on. Okay, this is our total emf. Now if you draw in signals, same thing, if you draw in signals, see what happens. To understand this, first you required cos omega t signal. What is cos omega t? How to draw cos omega t? Cos omega t first. If you understand, you can understand the complete signals very easily. Cos omega t means this is only, no? Cos omega t. Okay. This is 90 degrees. This is 0 degree. This is 90 degree. This is 180 degrees. Like this. Okay. Cos omega t. At cos 0 is what? 1. Cos 90 is what? 0. And so on. Cos 180 minus 1 and so on. So this is cos omega t signal. Then what is minus cos omega t signal? Because here we have minus cos omega t. That's why this is cos omega t. Then what is minus cos omega t? Minus. Just inverted of this, no? Minus means you will get simply like this. Inverted. Minus cos omega t. This is 90 degrees. This is omega t equal to 0. At omega t 0, cos 0, 1. But minus omega cos omega t, no, minus 1. And so on. This is minus cos omega t. Okay. Clear all of you how to draw minus cos omega t? Because directly if I draw, you may get doubt how it is. This is minus cos omega t. So first is fundamental. Then third harmonic. First I am drawing fundamental. Fundamental I am drawing first. Minus em1 cos omega t. So em1 is the magnitude minus cos omega t. It is like this. Okay. This is fundamental. Fundamental E1 this is. Okay. Now E3, this is E3. This E3 I have to draw. Cos 3 omega t, and it is minus cos 3 omega t. So in the same way, if you draw, you will get like this. This is 0 degree. This is a 90 degree. This is 30. This is 60. This is 30. This is 90. See, this is minus cos 3 omega t signal. I'm drawing. Check. Minus cos 3 omega t, like this you will get. Like this you will get. Okay. This is E3 signal. Minus EM1 cos omega t, E1. Okay. I have given how it is. In the same way, you have to analyze minus EM3 cos 3 omega t. This is EM minus EM3 cos 3 omega t signal. Third harmonic it is. Now, if you take the resultant of these two, check how we are getting resultant. Add these two signals. Add these two signals. Add these two. This is 90 degrees. This is 180 degrees. So add these two here. If you add these two, the resultant we get like this. So I have to draw this exactly. This is 180 degrees. So if I draw exactly, it is this is 90 degrees. See, at 90 degree, at 90 degree. So if you start from 0 degree, E3 is negative. This is also negative. So we'll get some negative here, some negative value, and then it is we are getting like this. Like this we get resultant of this two I am drawing. Fundamental EMF, third harmonic EMF. This is peaky wave only. This is like a peaky wave. So add these two signals. Draw exactly below that. You will get this waveform. I drawn side by. You draw below, exactly below this E1, E3. Draw exactly below this. You will get like this only. Okay. Now clear how EMF we are getting peaky wave. The shape of this EMF is peaky wave. Okay. Now what is the problem if you supply peaky wave to the loads? If EMF is peaky in the EMF induced in transformer is peaky, what is the problem? Yes, there is a problem. The problem is this magnitude of peak is very, very high. Actually, this is if it is sinusoidal, this is the peak. Let some EM it is. Let this EM is some 220, for example. But in this peaky, addition of third harmonic peaky and fundamental peaky, the overall peaky of this magnitude increase. The magnitude of this peak will increase. If it is 220 actually, now here it is 300 volts. Peak of the signal having magnitude 300, very high. If this voltage applied to the loads, your loads will damage because of this peaky voltage, suddenly high voltage due to that insulation of windings. If it is motor loads, for example, that insulation of that motor will damage or load will damage due to the problem of insulation. So we should not give this peaky voltage to the loads. So what is the voltage required for us from transformer? Purely sinusoidal voltage only required. So if you want to produce pure sinusoidal EMF or voltage, what should be the flux in core? Sinusoidal. If you want to produce sinusoidal flux, what should be the current in the winding? Magnetizing current, peaky wave. Okay, peaky wave. Peaky wave means it is having fundamental current plus third harmonic current. Then current is peaky, resultant current. Then flux is sinusoidal, EMF also sinusoidal. But what happens whenever current is sinusoidal? This one. If current is sinusoidal, flux is flat top, EMF is peaky. So that is I shown how it is. Okay. So again, from starting, I'm giving statements. Observe. Ideal case. Current flux both in phase. If current is sinusoidal, flux also sinusoidal. Then EMF induced in winding also sinusoidal. Okay, clear that is. Next, practical case. Practically, what is the shape of BH curve? Non-linear. So due to the non-linearity, we need to produce EMF is sinusoidal anyhow. For that, what should be the flux in core? We taken sinusoidal. So to produce sinusoidal flux, what is the shape of current we are getting? Shape of magnetizing current we are getting peaky wave. So if current is peaky wave, your flux in the core will become sinusoidal, EMF also sinusoidal. Clear up to this? Okay. Now, what happen if current is sinusoidal? If current is peaky, flux is sinusoidal, EMF is sinusoidal. But we are assuming, suppose current is sinusoidal. When current will is sinusoidal, suppose there is no third harmonic current, no, then current is sinusoidal only. If current is sinusoidal, what happens to shape of flux in the core? Flat top. That is, we have seen how it is. And if flux is flat top, what is EMF induced in winding? Peaky wave. So that is also we have seen how it is peaky wave. Now what is the problem of EMF peaky wave? If EMF is peaky, it is having highest magnitude at the peaks. That highest magnitude of the voltage will damage the insulation of windings. Insulation of loads, it will damage. So if load damage, do you sit calm in your home? Suppose your load damage due to some transformer problem, you got suddenly high voltage, then you will go to substation or electricity board immediately or not? Yes, because that is their problem. So they should take care of this. They are supplying non-sinusoidal voltage. So we don't want non-sinusoidal EMF. We want always sinusoidal EMF to operate our loads properly or smoothly. Okay, so these are the points. Now let's see what is the effect of this non-linearity in single phase transformer and three phase transformer, how it will affect. Okay, see that, right? Effect of non-linearity. So before that, I will use some two questions. See the question. See this question. Try to answer this. Read the question first. A single phase transformer fed from single phase air core transformer fed from a rated sinusoidal supply. Fed means supplied from a sinusoidal supply operating at no load. The steady state magnetizing current drawn by transformer from supply will have the waveform. Which is correct? Which option is right? Hmm. Most of you D, B, C, all mixed options you are getting. Observe carefully the question. You will get the exact answer. Observe carefully. Don't answer quickly. If any question looks very easy, take some time and answer slowly. Answer slowly. Most of you giving D, but answer for this question is C. Yes, some of you given C, right. Answer is C. Sinusoidal. C. Single phase air core transformer fed from sinusoidal supply operating at no load. The steady state magnetizing current drawn by transformer from supply. Actually, if it is a practical transformer, no. Practical also means important thing here, air core. That is you have to observe. Air it is, not iron core. Suppose if they don't mention anything, we will take iron only. But they given specifically air core. Air means, is there any non-linearity due to air? Is there any non-linearity due to air? No. Then if there is no non-linearity concept, then is the shapes of current and fluxes will change? No. So what is the shape of current? Sinusoidal. Sinusoidal only. If it is a iron core, then what is the shape of magnetizing current? Peaky wave. Which current that is? Option D. Okay, given here air core, so there is no non-linearity due to air, so the shape of current is sinusoidal as it is only. Okay, non-linearity is not applicable for air core, it is sinusoidal, whatever we given same sinusoidal only. Okay, yes, linear BH curve. Good. Next, similarly, see one more question. Try to answer this question. Try to answer this. Which is the answer? A single phase transformer fed from rated voltage supply at no load. The core loss of transformer assumed to be negligible. Core loss negligible means what is the corresponding IW term? Zero. Then no load current, or its no load current itself magnetizing current. What is the shape of that magnetizing current? Shape of magnetizing current is dash. Current drawn by transformer from supply means magnetizing current shape. What is that? Peaky. Now which is the option? Which peaky wave? B or C? Yes. Yes, all of you right. Option B is correct. The shape of magnetizing current is peaky wave. This is not this one. Maybe some of you may get this. See, no. Magnetizing current always peaky wave like this only it is. Peaky wave like this, but not C. If they ask exciting current, if they don't mention about core loss in the question, suppose core loss also there, then what is the total exciting current or no load current? I mu plus IW, both. Then if they ask suppose what is the no load current, the answer is C. Okay, here they are asking magnetizing current because iron loss is negligible. That means that only magnetizing current will be there. The shape of magnetizing current peak even. Clear? So today we will see only effect of this nonlinearity on single phase. So tomorrow we see three phase. Write that single phase first. Effect of nonlinearity on single phase transformer. Effect of nonlinearity in single phase transformer. Effect of nonlinearity in single phase transformer. How it will affect? What will be the shape of EMF in case of single phase transformer? Let's see that. Now, considering a single phase transformer, see this. Let this is the primary winding where source we are connecting. What is the source available for us? Always sinusoidal only. We don't have magnetizing current source directly, so we have sinusoidal source only. But observe how it will become peaky wave here. How it will become peaky wave automatically. See, applying a sinusoidal voltage source to the primary winding. Applying a sinusoidal voltage source V1 having frequency F. Okay. So whenever voltage source is sinusoidal, what is the current passing through that magnetizing current to create flux? Also sinusoidal only. So initially I mu sinusoidal, check. I mu is sinusoidal. Okay, because voltage source sinusoidal, current also sinusoidal. Now whenever there is a sinusoidal current in the winding, a flux will produce or not? Yes, the flux produced. What is the flux produced here? What is the shape of flux? Current is sine. What is the shape of flux now? Tell me quickly. What is the shape of flux produced in the core now? Yes, tell me quickly. Current is sinusoidal. So what is the shape of flux? Yes, flat top. Good. Flat top or trapezoidal shape, right? The shape of flux produced in the core is flat top. The shape of flux produced is flat top. Flat top flux means non-sinusoidal. It is having harmonics. Fundamental plus third harmonic. Flat top. Okay. Current is signed initially. Flux produced is flat top, which is having fundamental flux plus third harmonic flux. Other than non-sinusoidal, that may be flat top or peaky wave, anything having odd harmonics, 1, 3, and so on. But only 1, 3 we take, third harmonic and fundamental. 5, 1 plus 5, 3. Now, due to fundamental flux, an EMF induced in the winding, fundamental EMF E1. Okay. And due to third harmonic flux, an EMF induced in the winding E3. Okay. Fundamental flux will cause EMF. Third harmonic flux also will cause EMF. Now, this fundamental EMF is balanced by our supply voltage because supply is having fundamental only, that is purely sinusoidal signal. Okay. Fundamental EMF balanced by supply voltage, fundamental supply voltage. But this third harmonic EMF induced is not balanced with respect to source voltage. Why not balanced? Is there any V3 in supply voltage? No. Supply is purely sinusoidal. Then this EMF E3, E1 is balanced by voltage V1. Due to that, magnetizing current I mu is limited, sinusoidal. It is okay. But due to this third harmonic EMF, it is not balanced with any source voltage because V3 we don't have. Now what this E3 will do is, this E3 will cause a current within winding through the source. E3 will cause a current to flow through this because whenever there is EMF, a current will flow or not? Yes. So due to that E3, a current I3 will flow. Now this is a third harmonic current produced due to third harmonic EMF. Now I3 also flowing in the winding. Already I mu is what? Fundamental, sinusoidal, flowing. Now third harmonic also flowing. Now what is the shape of resultant current in the winding flowing? Therefore, the shape of resultant current I mu will become PQ. Okay. Now I mu is PQ. Once I mu becomes PQ, what is the flux produced? Sinusoidal. And what is then EMF induced under steady state finally? Sinusoidal. Now don't tell that once it is sinusoidal, E3 is 0, I3 is 0, then again I mu is sinusoidal. So this is a continuous process now. Under steady state, the EMF is sinusoidal. This is one way of understanding. Now see other way of understanding. Very easy it is. Due to fundamental, the flux produced is flat top, phi 1 plus phi 3. Okay. This fundamental flux is causing EMF E1. This third harmonic flux is causing EMF E3. And due to this E3, a current is circulating now, that is current I3. Okay. When there is a current I3 in the winding, it will produce one more flux, that is third harmonic flux or not. When there is a current, there is a flux due to that always. So due to I3, a flux phi 3 will produce. Now according to Lenz's law, this produced third harmonic flux will oppose the main flux, which is the reason for, what is the reason for phi 3? This phi 3 now. Initial current sinusoidal, flux flat top, phi 1, phi 3. Now due to that phi 3, E3 induced. Due to that I3, it is causing a current I3. Now due to that third harmonic current, a third harmonic flux is flowing. Now this third harmonic flux will oppose the cause. What is the cause for that? This phi 3. Now these two gets opposition, they cancel each other. So overall phi 3 finally becomes 0 or not? Yes. In the core, automatically third harmonic flux gets cancelled each other. So if third harmonic flux is cancelled, which flux is there in the core? Only fundamental flux is there. Then what is the shape of only fundamental flux? Is sinusoidal. So finally, what is EMF induced in the windings? Sinusoidal only. So is there any problem in single phase transformer due to nonlinearity? No problem at all. Automatically the EMF in windings is sinusoidal. So you can connect happily any load to single phase transformers. No problem for us. Okay. So write that points. Write that points. In case of single phase transformer with sinusoidal current, the flux produced is flat top. Comma, which causes EMF in the winding. EMF in the winding is peaky wave. EMF in the winding is peaky wave. In bracket E1 plus E3. Peaky wave means non-sinusoidal. Fundamental plus third harmonic EMF. E1 plus E3. Due to E3, that is third harmonic EMF, E3, a third harmonic current will circulate. So this third harmonic current, are you generating from source? No. Automatically third harmonic current will circulate in the winding. Because of closed path available, third harmonic EMF will cause a current, that third harmonic current circulating. So a third harmonic current will circulate in the winding, in addition to fundamental current. Fundamental means sinusoidal. In addition to fundamental current. Hence, the resultant current in the winding is peaky wave, because fundamental is flowing from source. Now third harmonic current also flowing because of that EMF E3 in the winding. So EMF in the winding is peaky wave. So once current is peaky, finally what is the flux produced in the core? Sinusoidal. EMF also sinusoidal. Okay. So there is no effect of this non-linearity in single phase transformer. No problem at all. The problem is only in case of three-phase transformer, because there we have two types of connection, delta and star connection. So that we will see in the tomorrow's class. Tomorrow also same time.
Good evening, sir.
Tell me, Shreyas.
Sir, in 50F, sir.
50.
50F, yes, sir.
Yes.
So why, in copper loss 2, why did you multiply by 1 square by 0.8 square, sir?
That is proportional to fraction of current only, na? Square of current. Because full load means X is 1 I taken. 80% means 0.8.
Okay, sir. You should multiply, always square it.
Because copper loss always proportional to square of current, but current is not given directly, but they given 80% full load. Full load means 1 I taken.
Okay, sir.
And 80% of full load means 0.8 only, no?
Okay, sir.
Like that.
Okay, thank you, sir.
So good evening, sir.
Tell me.
Sir, in 33F, sir.
30.
3, sir. 3.
Hmm.
Sir, not this, sir. Sir, 1. Sir, sorry, sir, I forgot the page number.
Which topic?
Sir, in that problem solving, we have solved before the break, no, sir. Before break, last problem. You also left us to do on
Already,
home.
I think the previous there only I'm not this one.
Sir, yes, sir.
Hmm.
There we are finding per unit regulation, no, sir.
Uh,
Sir, can you say in what cases we have to take per unit regulation and which cases we have to take percentage regulation?
so anything same formula only. Per unit regulation also what is the equation for per unit in resistance? Per unit resistance cos phi plus per unit reactance
Yes, sir.
sin phi. Same as it is percentage, no change. But why we use this equation here? Because in the question they did not given percentage or percentage x directly, no.
Yes,
They given resistance
yes,
values. So we calculated directly
yes.
by substituting that values here. That's it.
Okay, sir. Also, I started with because they have asked V1, I started with the primary equivalent circuit, sir.
Okay.
I solved that and I was wrong, sir. My answer was wrong.
Anywhere you can convert I1 R01 by E1 into cos phi. Anything you can take.
Oh,
Anyhow,
well,
percentage regulation you will get
substituting.
same. Hmm?
Okay, sir. Sir, while substituting in percentage, I mean per
Hmm.
unit regulation,
Hmm.
there I have to put I1 or not 1, no, sir, or not 1 divided
Yes.
by E1.
Yes. E1.
Okay, sir.
Oh.
And cos phi will not change according to the
No,
load,
no,
no, sir.
same.
It's same.
So load wherever it is primary or secondary, same, just transferring, no, same it is, no change.
Okay, sir. I will try one.
Hello, sir.
Tell me, Pratyush.
Sir, this sum only, sir, 55. I
Ah,
solved it in another way, sir. Like,
hmm.
I I2 కనిపెట్టాను సార్ ఫస్ట్.
ఎలా కనిపెట్టావు?
S is equal to VA cos phi ఉంది కదా సార్. రేటింగ్ పవర్ ఫ్యాక్టర్ ఇచ్చారు, మనకి లోడ్ వోల్టేజ్ ఇచ్చారు, KVA తెలుసు కదా సార్.
ఓకే.
I2 కనిపెట్టాను సార్.
I2 డైరెక్ట్లీ KVA బై వోల్టేజ్ వచ్చేస్తుంది కదా.
సార్ అంటే ఆ కాస్ పై పర్టికులర్ కాస్ పై దగ్గర
అది అసలు చేయబడలేదు, ఎందుకంటే అది డిపెండ్స్ ఆన్ లోడ్ యాక్టివ్ పవర్ కదా మనకి. డైరెక్ట్లీ KVA వోల్టేజ్ ఉన్నప్పుడు డైరెక్ట్లీ విల్ గెట్ సెకండరీ కరెంట్.
సార్ మరి ఆ పవర్ ఫ్యాక్టర్ వల్ల యూజ్ ఏం లేదు సార్ I2 కనిపెట్టడానికి.
ఓకే.
I2 సార్ అంటే లోడ్ అనేది 0.8 దగ్గర ఆపరేట్ అవుతుంది కదా సార్. సో మనం లోడ్ కరెంట్ నథింగ్ బట్ సెకండరీ కరెంట్ కదా సార్.
ఎస్.
సో సెకండరీ కరెంట్ నేను అలా కనిపెట్టాను సార్. S is equal to VA cos phi.
అక్కడ పవర్ అసలు ఇవ్వలేదు కదా, యాక్టివ్ పవర్ ఎంత అనేది.
ఓకే సార్. సార్ ఒకవేళ S is equal to VA సెకండరీ కరెంట్ రేటెడ్ కరెంట్ కనిపెట్టి దాన్ని ప్రైమరీలోకి మార్చుకొని R1 X1 తెలుసు కదా సార్. అక్కడ ఇంపెడెన్స్ డ్రాప్
ఎట్లయినా ఎస్, అది కూడా రైట్ ప్రొసీజర్, కరెక్ట్. ఎట్లయినా చేయొచ్చు
సార్. ఎంత డౌట్ సార్? ఓకే సార్, ఓకే సార్. నేను అది మర్చిపోయాను, అంటే VA cos phi సబ్స్టిట్యూట్ చేస్తాను.
ఓకే, పవర్ ఇస్తే మనం I2 ని అలా చేయాలి. KVA ఉన్నప్పుడు డైరెక్ట్లీ అది యూజ్ చేసి క్యాలిక్యులేట్ చేయాలి.
సార్ అది అక్కడ నేను అదే సార్ యాక్టివ్ పవర్ అనుకున్నాను సార్. ఎంత డౌట్ సార్? సార్ ఇప్పుడు మనం షార్ట్ సర్క్యూట్ టెస్ట్ చేసినప్పుడు ఎనర్జీ మీటర్ అనేది HPF వాడాం కదా సార్.
పవర్ వాట్ మీటర్.
సార్ అక్కడ ఈక్వలెంట్ సర్క్యూట్ బట్టి మనం అది లాగింగ్ పవర్ ఫ్యాక్టర్ అని చెప్పొచ్చు సార్. కానీ అది హై అనేది మనం ఎలా చెప్పగలం సార్? హై అనేది
అది ప్రాక్టికల్ గానే చెప్పాలి, కానీ డైరెక్ట్లీ మనం ఫిగర్ ని బట్టి చెప్పలేం కదా. బికాస్ ఆల్రెడీ వీ నో యాజ్ OC ఓపెన్ సర్క్యూట్ కేస్ పవర్ ఫ్యాక్టర్ ఈజ్ లెస్, మనం దాన్ని యూజ్ చేస్తున్నాం అంతే. షార్ట్ సర్క్యూట్ పవర్ ఫ్యాక్టర్
హై అని మనం అంటే థియరిటికల్ గా చెప్పలేమా సార్?
థియరిటికల్ గా నో, క్యాలిక్యులేషన్ ప్రాక్టికల్ క్యాలిక్యులేషన్ బట్టి అవి అంటే we can say that no load power factor if you know the values. Suppose transformer resistance reactance అన్ని తెలుసు అనుకో, under short circuit condition what is the power factor? R by Z. రెసిస్టెన్స్ ఆఫ్ ట్రాన్స్ఫార్మర్, ఇంపిడెన్స్ ఆఫ్ ట్రాన్స్ఫార్మర్, అది క్యాలిక్యులేట్ చేస్తే నీకు వాల్యూ వచ్చేస్తుంది. అండ్ నో లోడ్ కేసులో మనం ఫేజర్ డయాగ్రామ్ డ్రా చేసాం కదా.
ఎస్ సార్.
సో ఫ్రమ్ దట్ ఫేజర్ డయాగ్రామ్ యూ కెన్ టెల్ వాట్ ఈస్ ద నో లోడ్ పవర్ ఫ్యాక్టర్. అది లెస్ ఉంటుంది.
ఓకే సార్, ఒక డే 7 క్లాస్ లో మీరు బిఎం ఇస్ డైరెక్ట్లీ ప్రపోర్షనల్ టు V1/F లో V1 డిక్రీజెస్, F డిక్రీజెస్, బిఎం కాన్స్టెంట్ అని చెప్పారు సార్.
బిఎం ప్రపోర్షనల్ టు V1/F.
V1 decreases, F decreases in same proportion, so BM is constant, sir. అక్కడ మనం ఐరన్ లాసెస్ కనిపెట్టినప్పుడు మీరు అంటే ఐడబ్ల్యూ అనేది డిక్రీజ్ తీసుకున్నారు సార్. అంటే ఫస్ట్ ఒక నోడ్
అంటే కేస్ 1 లో హిస్టెరిసిస్ లాస్ ప్రపోర్షనల్ టు ఫ్రీక్వెన్సీ, ఎడ్డీ కరెంట్ ప్రపోర్షనల్ టు ఫ్రీక్వెన్సీ స్క్వేర్. అంటే మనం ఫ్రీక్వెన్సీ రెడ్యూస్ చేస్తున్నాం కదా, అదే కదా మనం ఇక్కడ అప్లై చేస్తున్నాం.
అవును సార్, కానీ మనకి మామూలుగా V1 డిక్రీజ్ అయింది కదా సార్, ఐ అనేది అంటే కాస్ బై డిక్రీజ్ అయింది, బి డిక్రీజ్ అయింది, అంటే ఐ మేబీ కాన్స్టెంట్ ఉండొచ్చు అని అస్యూమ్ చేసుకోవచ్చు కదా సార్ ఐడబ్ల్యూ అనేది.
అంటే ఐడబ్ల్యూ అనేది ఐరన్ లాస్ డిపెండెంట్ కదా.
అవును సార్, అంటే ఐరన్ లాస్ అంటే V0 I0 cos ∅0 కదా సార్. V1 ఆల్రెడీ డిక్రీజ్ అయింది కదా సార్.
V1 డిక్రీజ్ అయింది అంటే I0 ఇంక్రీజ్ అయ్యి ఉండొచ్చు కదా.
అంటే అవును సార్, అది అంటే I0 మనం డిక్రీజ్ అయింది ఎందుకు తీసుకోవాలని అంటున్నాను సార్. అంటే అక్కడ cos ∅ డిక్రీజ్ అయిపోయింది, V1 కూడా డిక్రీజ్ అయింది సార్. మళ్ళీ ఐడబ్ల్యూ కూడా డిక్రీజ్ అయిందని ఎందుకు తీసుకోవాలి, కాన్స్టెంట్ అని తీసుకోకూడదా అని.
అంటే నువ్వు డైరెక్ట్లీ I0 తీసేసుకుంటున్నావు, కానీ మనం I0 అనేది ఇంటర్నల్లీ సమ్ ఆఫ్ 2 కరెంట్స్ కదా, దాన్ని చూసుకొని కదా I0 కి పోవాలి.
అవును సార్,
డైరెక్ట్లీ I0 ఎలా చెప్తాం మనం వేరియేషన్.
అంటే సార్ సారీ సార్, ఐమ్యూ అనేది పెరుగుతుంది సార్, కానీ ఐడబ్ల్యూ అనేది కాన్స్టెంట్ ఉండొచ్చు కదా సార్ అంటున్నాను.
అది వేరీ అవుతుంది కదా, కానీ ఇప్పుడు ఈక్వేషన్ బట్టి మనం డైరెక్ట్లీ చెప్తున్నాం కదా. కేస్ 1 లో హిస్టెరిసిస్ లాస్ తగ్గుతుంది, ఎడ్డీ కరెంట్ లాస్ తగ్గుతుంది, అంటే ఓవరాల్ ఐడబ్ల్యూ కూడా తగ్గుతుంది.
ఓకే సార్, అంటే నేను
అంటే వోల్టేజ్ రెడ్యూస్ అవుతుంది, కరెంట్ కూడా రెడ్యూస్ అవుతుంది అనుకుంటున్నాను.
సార్ అంటే వోల్టేజ్ రెడ్యూస్ అవుతుంది కదా, అంటే వోల్టేజ్ పవర్ ఫ్యాక్టర్ రెండు రెడ్యూస్ అవుతుంది కదా, మరి అంటే మేజర్ అంటే 3 రెడ్యూస్ అయితే అది మేజర్ గా పడిపోద్ది కదా సార్. అలా అని అడిగాను సార్. అంటే
ఫేజర్ డయాగ్రామ్ ని బట్టి మనం క్యాచ్ చేయాలి ఫైనల్లీ. అంటే పవర్ ఫ్యాక్టర్ ఎలా చెప్తున్నావు నువ్వు, డైరెక్ట్ తగ్గిందని ఫేజర్ డయాగ్రామ్ డ్రా చేయబట్టి కదా చెప్తున్నావు.
అవును సార్, అంటే ఐమ్యూ ఇంక్రీజ్ అయితే ఇంకా ఐడబ్ల్యూతో కన్సిడర్ చేయకుండా పోనా ఫేజర్ కాస్ట్ డిక్రీజ్ అయిపోతుంది సార్. అంటే
ఐమ్యూ డిక్రీజ్, ఇక్కడ ఐమ్యూ కాన్స్టెంట్ కదా, ఎనీహౌ V1/F కాన్స్టెంట్ కాబట్టి ఐమ్యూ కాన్స్టెంట్ ఫస్ట్.
సార్ ఐమ్యూ ఫ్రీక్వెన్సీ డిక్రీజ్ ఇంకా ఐమ్యూ పెరుగుతుంది కదా.
V1/F కాన్స్టెంట్ కదా ఓవరాల్.
yes సార్.
బిఎం కాన్స్టెంట్ కదా, ఫ్లక్స్ కాన్స్టెంట్ అంటే ఐమ్యూ కూడా కాన్స్టెంటే కదా.
ఓకే సార్,
directly not decrease.
Okay sir. Sir, and the general doubt sir. Sir, same two transformer can have similar magnetizing characteristics sir?
Practically not possible, because maybe manufacturing defects undochu, material to material, core to core. Can you design same two transformers 100% identical? Maybe everything data is same, size is same, everything is same, but internally some difference will be there or not. Yes, in the operation while manufacturing, one transformer core staggering is good, other is not properly good, then definitely their properties will change. Okay,
అదే సార్, అంటే డిఫరెన్షియల్ రిలే కేసులో అక్కడ సార్ చెప్పినప్పుడు సేమ్ ఒక 2 ట్రాన్స్ఫార్మర్ కి సేమ్ మ్యాగ్నెటైజింగ్ క్యారెక్టర్స్ ఉండవు అని చెప్పారు సార్. సో అది అక్కడ ప్రొటెక్షన్ అని యూస్ చేస్తా అని చెప్పారు, అందుకు అడిగి.
yes.
ఓకే సార్, థ్యాంక్ యూ సార్.
Anil Kumar, tell me.
Sir, it's 67F, sir.
67F.
So that problems are next slide, 68. Sir, to produce sinusoidal wave means the IMU should be a peak wave, sir.
IMU?
Peaky wave, sir.
IMU peaky.
Yes, sir.
But here, what is the core? Air, no?
Yes, sir.
So air is not having any non-linearity concept, because air will saturate. No, air will never saturate.
Okay, sir.
That's why with air core, ideal case, like ideal case only we take. No saturation concept, no losses concept in air.
Okay, sir.
That's why. Sinusoidal only.
Okay, sir. Next slide, 69. Sir, could you please explain, sir, I did not get that.
A single phase transformer fed from rated voltage supply. The core loss of transformer is negligible. Means IW neglected, no?
Yes, sir.
Then what is I naught equal to I mu itself? Means
mu
magnetizing
itself.
current. So
Sir.
the current drawn by transformer from supply is only I mu.
Yes, sir.
Then what is the shape of magnetizing current practically?
So practically it should be sinusoidal, sir.
Actually sinusoidal. Just now I given effect. Observe what happens steady state.
Oh, yes,
Peaky
sir.
wave, no?
Peaky waves.
That is apply. That is apply now.
Okay, sir.
Clear?
Yes, sir. Got it, sir.
Okay.
Thank you, sir.
Sir, good evening, sir.
Yeah, Ravi Kumar, tell me.
Sir, last slide. సార్ ఇప్పుడు దీంట్లో రిజల్టెంట్ కరెంట్ అనేది పీకే వస్తుంది కదా సార్ ఫైనల్ గా అప్పుడు ఫ్లక్స్ అనేది మళ్ళీ సైనసాయిడల్ గా వస్తుంది సార్
ఫ్లక్స్ అనేది ఫ్లాట్ సైనసాయిడల్ అవుతుంది ఎస్ అంటే అదే థింక్ చేయకూడదు అలా సైనసాయిడల్ అయింది కాబట్టి మళ్ళీ ఓన్లీ 5-1 ఈస్ దేర్ నో 5-3 అంటే ఈ ప్రాసెస్ అనేది కంటిన్యూస్ ఇంకా
అంటే ఇప్పుడు ఇది ఈ వైండింగ్ అనేది పీకే వచ్చినప్పుడు సైనసాయిడల్ అది డౌట్
ఎస్ ఎస్ ఎస్
థ్యాంక్ యూ సార్
Hello, sir.
Tell.
Sir, my doubt is on regarding this last one only, sir. What you explained regarding this 5-3 flux, that is third harmonic flux.
Okay.
Sir, you did mention when you mentioned the first time regarding this peaky wave current, you did said that the peaky wave has both third harmonic and the fundamental component.
Yes.
So, but in this case of when you consider the reverse, that is if I mu is sinusoidal, what is the source of this third harmonic flux, sir? Where it is coming from?
It is coming from internal generated third harmonic EMF. No, nobody is supplying third harmonic automatically generating due to internal third harmonic EMF.
So it's automatically.
Yes, source is always sine only.
Okay.
After that, what is the flux in produced flat top?
Okay.
Now flat top flux is causing fundamental and third harmonic both. No.
Yes, sir.
Now due to the third harmonic, a current will circulate. That is the I3. Now through what that is circulating? Through source itself. Means what is the resultant current in the winding now? Peaky.
So peaky. So what I wanted was initially this flux generated have both the fundamental as well as the third component.
Yes, yes.
Initially, where the third component is coming from, sir?
Initially means?
Initially, like at the time of at the time when we assume that the I mu was sinusoidal.
I mu sinusoidal. Flux produced flat top, no? According to non-linearity. Non-linearity is there. Due to that, what is the flux is producing then? Flat top.
Okay. Okay, sir.
That is causing third harmonic EMF.
And this third harmonic itself will circulate and current, which itself makes it cancel itself. So
yes.
Negative feedback, like sort of.
Yes, yes. Lenz law.
Okay, sir. And sir, one more I had, that is like I couldn't ask it past for 5 days. This first day you took one problem regarding this triangle wave and stuff, sir.
Okay.
In that like I wanted to in that also use this mdi1/dt formula.
Yes.
My doubt was why can't we use this turns ratio, so like I2/I1 equal to N2/N1, that format, and solve it.
You can use, but what we want to find there?
The question asked was exactly to find the voltage across the load.
Okay, V2 suppose.
Yes, sir. And the given equation, if you see, it was 10 sin 100 pi t. That is a current.
Okay, 10 sin
100 pi t.
100 pi t. Okay, current it is.
Yes, sir. They asked the secondary load voltage.
And any number of turns are given?
No, sir. They just gave the magnetizing inductance as 400 by pi millihenry. Yeah. It is a 1:1
M given, IV given. Then directly M into di1/dt only, no formula.
Yes, sir. And in the diagram, it was mentioned it as a 1:1 transformer.
Okay, no problem. Means E2 equal to M di1/dt.
Okay, sir.
Then you can find M value given.
Yes, sir. That is 400 by pi millihenry.
Then directly you can use this equation m di by dt. But
That's one method what you taught, sir. What I'm asking, if we use E2 by E1 equal to N2 by N1, I'm getting 300 volts, sir.
E2 by E1 equal to
N2 by
N2 by
N1.
N1.
And since N2 by N1 is
1 is
something
to
like
1.
1:1.
Okay, then E2 equal to E1 na directly.
And then if I differentiate it, sir. No, I did something else.
Now check the question once properly where what it is given. You can use E2 by E1
Oh,
equal
sorry,
to
sir.
N2 by N1.
I used I2 by I1 equal to N2 by N1, sir.
No, I2 by I1 equal to N1 by N2, no?
Still it is 1:1, so it doesn't matter, no, sir. I2 equal to
Okay,
I1.
okay. Then I2 equal to I1. But what they want to find?
They asked me to find VAB. That is a voltage across the load.
Then I2 you will get. Then what is the voltage current into that impedance? If impedance
Yes, sir.
is there,
And
then
the
you can do
impedance
that.
is 30 ohms.
No, you can multiply with that.
Sir, if you multiply that, it is 30 ohms. Peak value is 10 amps. So if you multiply, you're getting 300 volts. But if you use MDI by dt, you're getting max value is 400 volts. So which one to trust?
Here current how much? Peak value?
10 amps, sir.
Peak value, no, that is.
Yes, sir.
Then RMS value how much? Im by root 2.
7.07.
Then multiply with that. How much you are getting?
Somewhere if you multiply it with 30 ohms, you will get around 210.
Maybe that is wrong. So two different how will come.
Yes, sir. So that question framing is wrong, right, sir?
Yes.
All right, sir. That was all I wanted to ask. Thank you, sir.
Okay. Rakesh.
Sir, good evening, sir.
Tell Rakesh.
Sir, like we have got flat top curve, no, sir, flux, sir. Sir, it's becoming constant in the mid part, no, sir. Can I say that transformer got saturated at that particular point, sir?
Not there, because so in the flat top we cannot say where it's saturated, because it is not having exactly flat, no, there it is having like a dip, like this.
Yes, sir.
Not saturated.
Okay. Can it be made saturated, sir, like by making it constant, like in synchronous machines we make, no, sir?
Here also we have core, every core will saturate now. So there, that is what BH, or if you draw flux versus current I mu, whenever current increase, flux increase, after that saturation. Why saturated? Every core will saturate, no, that is.
Yes, sir. It particular. Okay,
like
sir,
that approximately you can get trapezoidal shape only. Okay.
Yes, sir. Sir, in the same slide, sir, can you explain this? Like flux is equal to flux 1 plus flux 3. That after that once can you explain, sir?
Flux is?
In the same slide, you wrote flux is equal to fundamental third harmonic.
Phi equal to phi 1 plus phi 3, and this phi 3 is causing a EMF E3.
Yes,
due to that E3, I3 will produce.
Yes, sir.
I3. A current I3 is flowing.
Yes, sir.
Due to that current I3, a flux will produce again or not?
Yes, sir.
That is phi 3. Now, according to Lenz's law, the produced flux should oppose the cause. What is the cause for phi 3? This actual phi 3.
Yeah.
Now, these two gets cancelled each other. Then finally, phi 1 only will be there in the core. So, EMF is sinusoidal.
Okay. So, doubt maybe silly, sir. Like E1 won't produce like current, that will be a magnetism.
E1 will produce, but that E1 is balanced by source voltage, no?
Source voltage.
If V1 is not there, E1 will cause a current. But V1, E1, current I mu is what? V1 minus E1 difference. Based on that, I mu is decided.
Yes, sir.
That's why separately a current we don't take for E1 again.
Okay, sir. Thank you, sir.
Okay.
Sir, good evening, sir.
Sure.
Once open the regulation curve, sir.
Slide number, not like that. Where it is?
Before the సో 0.9 తర్వాత 1 అని కన్సిడర్ చేసుకొని మనం తీసుకుంటాం కదా, 0 ఎందుకు కన్సిడర్ చేసుకొని తీసుకున్నారు సార్?
సెంటర్ లోనో?
0.9 తర్వాతకి 0 అని మెన్షన్ చేశారు కదా సార్.
అంటే జనరల్లీ దిస్ జీరో రెగ్యులేషన్ మనకి ప్రాక్టికల్ గా వచ్చేది బిట్వీన్ 0.9 అండ్ యూపీఎఫ్ మధ్యలో వస్తుంది. అందుకనే నేను 0.91 కి మధ్యలో 0 చేశాను.
అంటే మళ్ళీ ఇక్కడ లెఫ్ట్ సైడ్ లో కూడా 0 నుంచి కన్సిడర్ చేసుకున్నాం కదా సార్, అందుకనేసి.
లెఫ్ట్ ఏంది కింద నెగిటివ్ నా?
లేదు సార్, సి అని రాశారు కదా సార్ ఇక్కడ లెఫ్ట్ సైడ్ లో 0.2, 0.4, 0.6, 0.8
అంటే
నుంచి
ఇది
వస్తుంది.
పవర్ ఫ్యాక్టర్స్ కదా, వాల్యూ ఆఫ్ పవర్ ఫ్యాక్టర్ 0 పవర్ ఫ్యాక్టర్, 0.2 పవర్ ఫ్యాక్టర్. ఇది
పోతే
0
యూనిటీ
రెగ్యులేషన్
పవర్
కాదు.
ఫ్యాక్టర్ 1 ఉంటది కదా సార్.
ఆ?
యూనిటీ పవర్ ఫ్యాక్టర్ 1 కదా సార్ లాస్ట్.
యూనిటీ పవర్ ఫ్యాక్టర్ ఇక్కడ కదా సెంటర్ లో తీసుకున్నాం కదా యూనిటీ పవర్ ఫ్యాక్టర్. ఇది 1. దిస్ ఈజ్ 1 యూనిటీ పవర్ ఫ్యాక్టర్ రెసిస్టివ్ లోడ్. ఓకే.
0.9 to 1 మధ్యలో 0 తీసుకుంటాం
ఎస్
సార్.
ఎస్.
ఎందుకు సార్ అట్లా తీసుకుంటే, అంటే ఏమవుతుందో తీసుకుంటే అట్లా?
మనకి మనం ఫేజర్ డయాగ్రామ్ లో అబ్జర్వ్ చేసాం కదా ఇప్పుడు,
Yes, sir.
యూపీఎఫ్ లో పాజిటివ్ వాల్యూ వచ్చింది రెగ్యులేషన్. సో ఇలా మనం కరెంట్ ని లీడ్ చేస్తూ ఉంటే ఎట్ 1 పవర్ ఫ్యాక్టర్ లో మనకి 0 అవుతుంది కదా రెగ్యులేషన్. సెకండ్ కేసులో ఇక్కడ బిలో. ఓకే.
ఓకే సార్.
అంటే ప్రాక్టికల్ గా అవి తెలిస్తే మీకు అర్థమవుతుంది. ప్రాక్టికల్ చేసేటప్పుడు మనకి 0 రెగ్యులేషన్ అనేది ఈ 0.91, 0.92 ఆ రేంజ్ లోనే వస్తాయి 0 రెగ్యులేషన్ అని. అందుకే మనం అక్కడ డ్రా చేసాం బేస్డ్ ఆన్ ప్రాక్టికల్ అనాలిసిస్.
ఓకే సార్.
ఓకే
సార్, నో లోడ్ కరెంట్ హైగా ఉంటుందా లేకపోతే ఫ్లక్స్ కరెంట్ హైగా ఉంటుందా సార్?
నో లోడ్ కరెంట్,
నో లోడ్ కరెంట్ ఈజ్ హై ఆర్ ఫ్లక్స్ కరెంట్ ఈజ్ హై సార్?
ఫ్లక్స్ కరెంట్ అంటే మ్యాగ్నటైజింగ్ కరెంట్ కదా. I0 is more కదా. I0 is little greater than IMU. I0 is sum of two currents, IMU and IW.
ఇంతకు ముందు కర్వ్ డ్రా చేసాం కదా సార్, I0 నో లోడ్ కర్వ్ డ్రా చేసాం కదా సార్. అందులో మరి నో లోడ్ కరెంట్ స్పీడ్ తక్కువ ఉంది అని చెప్పారు కదా సార్.
నో లోడ్ కరెంట్,
నో లోడ్ కరెంట్ తక్కువ ఉంది కదా సార్ ఫ్లక్స్ కరెంట్ కన్నా.
ఫ్లక్స్ కరెంట్ అంటే వాట్ ఈస్ దట్? IMU నా?
Sir.
Which current? This is IMU, this is IW, and sum of these two we call no load current. Then which one?
కర్వ్ సార్ ఇంతకు ముందు డ్రా చేసాం కదా సార్ మనం.
Slide number.
పార్షియల్ ట్రాన్స్ఫార్మర్, ఆపరేషన్ ఆఫ్ ట్రాన్స్ఫార్మర్ నాన్
Starting. Okay. దీంట్లోనూ ఐడియల్ కేస్ ఆర్ ప్రాక్టికల్?
ఇక్కడ సార్ I0 అనేది తక్కువ ఉంది కదా సార్ ఫ్లక్స్ కన్నా.
దట్ ఈస్ ఓకే. యూ టేక్ సేమ్ ఆల్సో బికాస్ ఫ్లక్స్ అనేది డిఫరెంట్, కరెంట్ అనేది డిఫరెంట్ కదా. ఫ్లక్స్ సిగ్నల్, కరెంట్ సిగ్నల్, దట్ ఈస్ యువర్ ఆస్కింగ్. అది నాట్ ఏ మ్యాటర్, ఎక్కడైనా డ్రా చేయొచ్చు మనం. సో జస్ట్ టు షో బోత్ హ్యావింగ్ అటైనింగ్ సేమ్ పీక్ ఎట్ సేమ్ ఇన్స్టెంట్, దాన్ని అలా డ్రా చేశాను అంతే. కరెంట్ అనేది డిఫరెంట్, ఫ్లక్స్ అనేది డిఫరెంట్ సిగ్నల్స్ కదా.
అంటే నో లోడ్ కరెంట్ ఎందులో అయినా కానీ అదే హై ఉంటుంది కదా సార్, వేరే దాంట్లో వచ్చుకుంటే అట్లా అనేసి నేను అడుగుతున్నాను.
అలా ఏం లేదు, మనకి కరెంట్ సిగ్నల్స్ ఎలా అయినా రిప్రజెంట్ చేయొచ్చు బికాస్ ఫ్లక్స్ అనేది డిఫరెంట్ యూనిట్ కదా కంప్లీట్ గా. వెబర్స్, కరెంట్ మనం ఆంపియర్స్ మెజర్ చేస్తున్నాం. సో బోత్ ఆర్ డిఫరెంట్.
సార్ మినిట్ స్లైడ్ ఒకసారి ఓపెన్ చేస్తాను.
Which one?
1 minute sir. నేను ఒక క్వశ్చన్ అడిగాను కదా సార్.
ఏది అది?
Hello sir.
Who is this?
You.
Charan. Charan?
No sir, Kushal it is.
Kushal, tell me.
Sir, in the problem we have seen that the 2200 to 220 volt, we have seen the new voltage is equals to old voltage plus the voltage drop. Means 220 volt in the load we want. So in the primary side we have increased the voltage, sir. 2200. So how could we increase the voltage? Means it is the rated voltage na?
Rated means how much you are increasing there, tell me first.
So drop
29 volts only, no, that is not problem. But you should not increase like hundreds of voltage, then insulation problem may get. But for small 20-30 volts, no problem.
Okay, sir.
Okay.
Sir, voltage regulation in a slide open there, sir. Note 2.
Case 1 or case 2?
Note 2, sir. Case 1 panel, sir.
This one?
No, sir. No, sir, before that. 30 slides, sir. Sir, ఇక్కడ లీడ్ పవర్ ఫ్యాక్టర్ 3 కేసెస్ యూజ్ చేస్తున్నాం కదా సార్. లీడ్ పవర్ ఫ్యాక్టర్ కన్నా ఎక్కువ యూపీఎఫ్ ఉండదు కదా సార్, దాంట్లో 3 కేసెస్
యూపీఎఫ్
ఎక్కువ కదా సార్, పవర్ ఫ్యాక్టర్ యూపీఎఫ్ ఎక్కువ కదా సార్. 1 లీడ్ పవర్ ఫ్యాక్టర్ కన్నా లీడ్ పవర్ ఫ్యాక్టర్ లో 3 కేసెస్ యూజ్ చేస్తున్నాం కదా సార్, 0 పాజిటివ్ నెగటివ్. మరి యూపీఎఫ్ లో కూడా యూజ్ చేస్తాము.
అంటే ద మీనింగ్ ఈజ్ నాట్ దట్ వన్. అంటే మనకి యూపీఎఫ్ దగ్గర వచ్చే రెగ్యులేషన్ ఒకటే వస్తుంది కదా, ఒక పవర్ ఫ్యాక్టర్ దగ్గర ఒకటే వస్తుంది. యూపీఎఫ్ అంటే 1. అంటే లీడింగ్ లో మనకి డిఫరెంట్ పవర్ ఫ్యాక్టర్స్ ఉన్నాయి కదా, మళ్ళీ 0.8, 0.7, 0.6 అలాంటివి. లీడ్
లాగింగ్ లో అయితే తీసుకోవట్లేదు కదా సార్.
లాగింగ్ లో కూడా ఉన్నాయి కదా, 0.8, 0.6 లాగింగ్, 0.5 లీడింగ్, లాగింగ్ అండ్ సో ఆన్. లాగింగ్ మీన్స్ వాట్? సపోజ్ దిస్ ఈజ్ వోల్టేజ్, this is voltage V2, and UPF means current is in phase with voltage. Idi UPF power factor. Lagging ante idi lagging e kada, current I2 lags, idi kuda lagging e kada, idi kuda lagging e kada, ivanni lagging e kada up to 90 degrees. So lagging lo different power factors vastayi again. Alage leading lo kuda you will get different power factors up to 90 degrees. Ani UPF anedi okate kada. Okay.
Hello, sir.
Tell, Charan.
Sir, in page number 56, sir. Tell me. Sir, I did not understand this problem, sir. How you for
see first
V1 new
what
is equals to?
Actually, according to given data, what is the primary voltage? 2200.
2200.
Now E1 also same, now 2200. Why no drop here? Because total resistance reactance we are considering on secondary side. Then is it clear? Both are same?
Yes, sir.
Then E2 will be 220. Then actually how much V2 you will get? Less than 220 only now. That means how much you will get? Suppose for example 210, for example. Clear up to this?
Yes, sir.
But what is they want in the question? At the load itself they want 220.
Yes, sir.
That means if it is 220, this voltage should increase or not? E2 more
Yes,
than
sir.
220 it is. If it
Yes,
is
sir.
more than 220 means E1 also should be more than 2200 or not?
Yes, sir.
That means V1 also more than 2200. So
Okay.
how much more that is? That is whatever voltage drop is taking place, that we need to increase additionally there. So that is we calculated voltage regulation for this, and whatever percentage regulation we got, that much voltage additionally we added whatever drop is taking place.
Okay, sir. Sir, can we do like this?
Okay.
Like
Okay,
finding current
read
in
one more
primary.
time.
Hello, sir.
Finding current in?
Sir, can we do like finding primary current and finding losses in primary like that, sir?
Not losses, because this complete depends on voltage drop only, no? So no need to find losses here. Voltage drop. So you can refer complete circuit to primary also. Like that also you can solve.
Okay, sir.
See, if you like this also means let here. I'm considering total drops referred to primary side like this, R01, X01. Okay. Now this is
Okay.
secondary no drop. Now
Yes, sir.
E2 is 220, V2 also 220, both same. For that reason, what is the E1 value? 2200. Now calculate V1, how much V1 required, apply R01, X01. Now calculate I1, okay, and try to find V1 here. Like that also you can solve.
Yes, sir. Sir, I told this one only, sir.
Okay.
Finding E1 and yes, sir. Voltage drop.
You can find like this also. Anyway, because we are going there with the standard calculating regulation. Like this also you can solve. Just voltage drops, night is.
Okay.
Okay.
So here the
Tell.
here they gave resistances values.
Sir. Sir.
Who is this?
Hello, sir.
Ranganatheshwaran. Charan.
Sir, they gave resistance values only for finding this percentage hour, no, sir. Percentage hour and X0 one.
Yes.
Okay, sir.
Now tell me.
Sir, good evening, sir.
Teja, tell me.
Sir, ఇది పవర్ ట్రాన్స్ఫార్మర్ కి పవర్ ఫ్యాక్టర్ ఎట్లా డిఫైన్ చేస్తారు?
Transformer power factor means based on its resistance and reactance, R index.
Sir, ఇప్పుడు లోడ్ కూడా ఉంటది కదా సార్. సపోజ్ లోడ్ కూడా ఉంటది కదా.
Then it is depend without load based on resistance and reactance. Otherwise, if load is connected, that is only we consider load power factor.
Only load we consider, sir.
Yes.
Sir, ఇప్పుడు R0 to X02 మరి
అవి రెసిస్టెన్స్ కదా, ట్రాన్స్ఫార్మర్ వైండింగ్ రెసిస్టెన్స్ అండ్ రియాక్టెన్స్.
సార్ అంటే ఇప్పుడు 2 పవర్ ఫ్యాక్టర్స్ ఉంటాయి సార్. ఇప్పుడు లోడ్ పవర్ ఫ్యాక్టర్ and transformer different.
Suppose you forget regarding this. Previously in load operation we have seen, if load is having some power factor, secondary power factor kuda ade kada. Then primary power factor is little change. So that we have seen again in the load operation, no? So here what we are finding is X by R of transformer, X by R of load. Why we are calculating? Now, in order to have maximum regulation at what power factor? Similarly, where we get zero regulation. So adi calculate cheyadaniki manam use chestunnam. That's it.
జనరల్ గా సార్ అంటే ఇప్పుడు జనరల్ పవర్ మనకి క్వశ్చన్స్ లో పవర్ ఫ్యాక్టర్ ఇస్తారు కదా సార్. అది ఎట్లా క్యాలిక్యులేట్?
That is load only we have to take.
Only load, sir.
Yes.
Okay, thank you. That's
Sir.
Ranganatheshwaran.
Sir, 63F slide, sir.
63F.
Sir, here we added harmonic and fundamental current now, sir. In third harmonic, we took it as a negative direction. So
because third harmonic current will be in opposite direction to fundamental.
But some other cases we took it as a normal only.
That you will get if you have good idea.
62F. We took it as a normal third harmonic.
Okay, just I have shown here third harmonic, fifth harmonic randomly like this. So you go and read in signals and system about Fourier series analysis completely. There you will understand how to draw these signals there.
Okay, sir.
Okay.
Okay, thanks.
Okay.
Sir, in 34F, sir. సార్ ఇక్కడ ఇది ఒకసారి మళ్ళా చెప్పరా సార్, రెగ్యులేషన్ లాగ్ పవర్ ఫ్యాక్టర్ కంటే ఎందుకు తక్కువ అని?
Whenever lagging లో ఉన్నప్పుడు E2 magnitude ఎంత ఉంది చెక్ చేయండి ఒకసారి. ఇది లాగింగ్ కదా. వాట్ ఈస్ E2? కరెంట్ I2 ఇక్కడ ఉన్నప్పుడు E2 magnitude ఎంత ఉంది? ఎక్కువ ఉంది కదా. అప్పుడు డిఫరెన్స్ ఏమవుతుంది? ఎక్కువ వస్తుంది. దట్ ఈస్ మోర్ పాజిటివ్. అదే యూపీఎఫ్ లో ఈ కరెంట్ ఎప్పుడైతే ఇలా షిఫ్ట్ అయిందో యూపీఎఫ్ కి ఈ E2 అనేది తగ్గిపోయింది కదా. magnitude ఆఫ్ E2 తగ్గితే డిఫరెన్స్ కూడా ఏమవుతుంది?
తగ్గుతుంది.
So reduces.
Sir, in 21F, sir, in yesterday's class, 21. సార్ ఇక్కడ డిస్ట్రిబ్యూషన్ సైడ్ అంటే మీరు రాశారు కదా సార్, లోడ్ దగ్గర మనం ట్రాన్స్ఫార్మర్ 11 kV బై 400 వోల్ట్స్ పెడతామని. అక్కడ సెకండరీ సైడ్ లో 400 వోల్ట్స్ ఉంటే అప్పుడు ఎక్కువ కరెంట్ వస్తుంది కదా సార్, మళ్ళీ లోడ్స్ కంటే ఎక్కువ కరెంట్ వెళ్ళిపోతే
అంటే పవర్ రేటింగ్ తక్కువ ఉంటుంది కదా ట్రాన్స్ఫార్మర్. అలా కాదు, పవర్ రేటింగ్ తగ్గిపోద్ది కదా. అంటే లో వోల్టేజ్ కాబట్టి హై కరెంట్ అంటే ఎంత హై కరెంట్, ఆ కెపాసిటీ దానికి ఉంటుంది కదా, దాని లిమిట్.
అంటే ఇప్పుడు పవర్ రేటింగ్ అనేది దానికి తక్కువ ఉంటుందా సార్ డిస్ట్రిబ్యూషన్ సైడ్?
హై కరెంట్ అన్నా కూడా కరెంట్ అనేది ట్రాన్స్ఫార్మర్ సప్లై చేయదు. మనం వాట్ ఎవర్ ద లోడ్ వి కనెక్టెడ్, లోడ్ విల్ టేక్. లోడ్ కి ఎంత అవసరమో అదే తీసుకుంటుంది.
ఓకే సార్. మళ్ళీ సార్ మీరు పవర్ ట్రాన్స్ఫార్మర్ కి ఎక్కువ ఎఫిషియన్సీ ఉంటుంది అన్నారు కదా సార్, మోర్ ఎఫిషియన్సీ వై సార్ వెన్ కంపేర్డ్ టు డిస్ట్రిబ్యూషన్ ట్రాన్స్ఫార్మర్?
అవుట్పుట్ ఎక్కువ ఉంటుంది కదా ఆల్వేస్
పవర్ ట్రాన్స్ఫార్మర్ సార్.
ఎగ్జాక్ట్లీ మనం చెప్పలేము, అది క్యాలిక్యులేషన్ బట్టి చెప్పాల్సింది. ప్రాక్టికల్ డైరెక్ట్లీ వి కెనాట్ షో.
సార్ ఇంకోటి ఎస్సీ టెస్ట్ లో మీరు వోల్టేజ్ 5 to 10% అప్లై చేయాలన్నారు కదా సార్. ఒకవేళ ఎక్కువ వోల్టేజ్ అప్లై చేస్తే కరెంట్ తక్కువ ఉంటుంది కదా సార్, అప్పుడు వైండింగ్స్
షార్ట్ సర్క్యూట్ లో ఉంది కదా, హై వోల్టేజ్ మీరు ఇంక్రీజ్ చేసే కొద్దీ కరెంట్ కూడా ఇంక్రీజ్ అయిపోతుంది షార్ట్ సర్క్యూట్ కాబట్టి.
సెకండరీ సైడ్ షార్ట్ సర్క్యూట్ ఉంది కదా సార్, ప్రైమరీ ఏం ఎఫెక్ట్ అవ్వదు.
అదే కదా, ఇప్పుడు ప్రైమరీ అనేది సెకండరీ మీదగా డిపెండ్ అవుతుంది. ఎప్పుడైతే మనం సెకండరీ షార్ట్ చేస్తామో హై కరెంట్స్ వల్ల ప్రైమరీ కూడా హై కరెంట్ అవుతుంది. ట్రాన్స్ఫార్మర్ యాక్షన్ అదే కదా, సెకండరీ ఇంక్రీజ్ అయితే ప్రైమరీ కూడా ఇంక్రీజ్ అవ్వాలి.
అంటే ఇప్పుడు సెకండరీలో ఎక్కువ ఉండడం వల్ల ప్రైమరీ కూడా ఎఫెక్ట్ అవుతుందన్న సార్?
yes
ఓకే
సార్. tell Mohammed
sir. Sir, this page 56F, sir. Problem we have solved now, sir. 2200 by 220.
56.
56. Sir, here we have taken that V1 plus percentage regulation into V1. How we got that formula, sir?
V1?
The new supply voltage is equal to V1 in a old supply voltage.
How
plus
we got that is a given shortcut to find like that easily, because once you find regulation, whatever voltage drop is there, see that much voltage drop we need to compensate. So for that reason I given a small equation easily to find like this.
Sir,
otherwise
I solved it by KVL with respect to primary, with respect to secondary, but in all cases I am getting 2233, sir, not 2229. And the another option we have 2236. It is near to that one. I've did all with all decimal points and all up to 3, 3, 4, 4 places.
Okay, you send it once, I will check. Okay.
Sir, this last topic अपन डिस्कस करें ना सर, नॉन लिनियरिटी ऑफ कोर. इसमें I नॉट को अपन I म्यू प्लस IW डिवाइड करें ना सर.
This one? This
practical transformer. Question है sir, practical transformer.
Okay. Yeah.
ये सर. सर ये बॉटम में वेव फॉर्म कैसा लिया सर अपन? I mu or IW?
I mu, this is just addition of two signals directly given. ये दो ऐड करने से ये सिग्नल आ जाएगा ना?
हाँ सर.
वही है. So
नहीं सर, आप साइन और कॉस इसकी ऐसा आया बोल के कुछ एक वर्ड्स इस्तेमाल करें, इसके लिए कुछ क्वेश्चन.
So this is I taken directly from standard books because there is so much again equations, but these are all not required. ये सब नहीं चाहिए.
अच्छा, ओके.
बिकॉज ये करंट को शो करने के लिए टू करंट सिग्नल होना चाहिए, इसीलिए दो सिग्नल में एडिशन करने से ये सिग्नल आ जाएगा ना.
हाँ सर, वो तो क्लियर है.
वो तो बस
सर ये पूरा नॉन लिनियरिटी में सिर्फ अपने को मैं 3 पॉइंट्स बोलता हूँ सर, इसको क्या तो ऐड करना है तो बोला. अगर मैग्नेटाइजिंग करंट साइनसॉइडल रहे तो फ्लक्स क्या कि फ्लैट टॉप ईएमएफ पी की.
अगर मैग्नेटाइजिंग करंट साइनसॉइडल
है,
yes.
फ्लक्स क्या है कि फ्लैट टॉप ईएमएफ पी की. सेकंड केस अगर मैग्नेटाइजिंग करंट पी की है तो फ्लक्स साइनोसॉइडल, EMF भी साइनोसॉइडल।
yes right।
और ये थर्ड पॉइंट क्या है कि सिंगल फेज ट्रांसफार्मर में अपन अगर साइनोसॉइडल फ्लक्स है तो भी उन्हें ऑटोमेटिक ठीक ही कर लेता है उसको।
yes automatically
बस ये 3 पॉइंट्स है ना सर, या और एक्स्ट्रा
yes
पॉइंट्स
yes नहीं नॉट रिक्वायर्ड। 3 फेज ट्रांसफार्मर में वो 3 फेज वाइंडिंग पे डिपेंड करेगा, डेल्टा और स्टार। सो टुमारो वी सी क्लियरली दैट। ओके
नहीं, ये डेरिवेशन पूरा तो कुछ समझ में नहीं आया, लेकिन
नहीं नॉट रिक्वायर्ड। यही बहुत लोग को समझ में नहीं आएगा ना पहले, अभी ज्यादा करने से पूरा
हाँ
चले
सर,
जाएगा।
लेकिन थोड़ा क्लियर, हाँ क्लियर तो है सर, थैंक यू।
ओके anybody else? Ajay you want? Maybe Teja you want? Ajay
Hello, sir.
tell Ajay
Sir, due to a network problem, I can't hear regulation curve, sir.
page number?
Sir, forget, sir. I don't know. Regulation, corner, sir, lead, lag, unity power factor, both are come, and 3 are command.
Okay. Tell.
I did not understand how we.
So
How
this
can
is
you?
drawn from previous 3 cases. So did you attend previous 3 cases exactly completely?
Yes, sir.
Oh, in case 1 lagging power factor, what is the regulation always? Positive, no?
Positive, sir. Yes, sir.
Now at UPF, what is regulation? Positive.
Positive.
Okay, so this is I taken positive at UPF first. Now
Okay.
if you go from UPF towards lagging side, regulation what happened? Increase.
Negative, sir.
Positive increases.
Yes, sir.
Increases. So that is I drawn. Now same you come from UPF to leading side. What happens to regulation? Slowly decreases, no?
Yes, negative side.
Negative 0 and then negative. That is I drawn.
Okay, sir. Thank you, sir.
Teja?
Thank you.
Okay, right.
Hello, sir.
Teja, tell me.
Sir, one point. Okay.
Tell.
Sir, 1 point, sir. Sir,
tell.
non-linearity of is not applicable for air core transformer. 1 point is there, na sir?
Yes, not applicable.
sir, why sir?
Because
कोर में सैचुरेशन होता, इसलिए
इसमें एयर में कुछ नहीं होता ना, नो लॉसेस, नो सैचुरेशन, नथिंग। सो वो आइडियल केस ही है।
एयर में सैचुरेशन नहीं होता।
हाँ, एयर में कितना फ्लक्स लाइन
एरिया,
फ्लक्स लाइन कहाँ सैचुरेट होता? फ्लक्स कुछ एरिया हैगा एरिया में, एयर में
नहीं रहता।
इसलिए
मतलब सर एयर कोर बोले तो भी एक नॉन डायलेक्ट, मतलब
यस
क्या एक वुड को कोर के ऐसा इस्तेमाल कर लेते तो उसको नॉन एयर कोर ही बोलते ना सर?
वुडन नो वो वुड तो कंप्लीट डिफरेंट है ना,
नॉन परमिएबल मटेरियल सर,
डायमैग्नेटिक।
हाँ उसको डायमैग्नेटिक मटेरियल को कोर कैसा इस्तेमाल करे तो वो एयर कोर रहता ना।
ऑलमोस्ट रिलेटिव पैरामीटर सेम नहीं है, लेस देन 1। Any other?
Hello, sir.
Teja, tell me.
సార్ ఇది కంప్లీట్లీ అవుట్ ఆఫ్ అదే మెషిన్స్ సబ్జెక్ట్ కాదు సార్, ఇప్పుడు నేను అడిగే డౌట్ ప్రాక్టికల్ సార్.
ఏదైనా అడుగు
సార్. ఇప్పుడు మన ఇంటికి మన హౌస్ ఉంది కదా సార్, మా హౌస్ లో 4 రూమ్స్ ఉంటాయి సార్. 4 రూమ్స్ లో ఫస్ట్ 2 రూమ్స్ కి మెయిన్ ఒక మెయిన్, నెక్స్ట్ 2 రూమ్స్ కి ఇంకొక మెయిన్ సార్. హలో సార్.
ఓకే.
ఇప్పుడు ఫస్ట్ రూమ్ యొక్క మెయిన్ ని ఆపేసి సెకండ్ మెయిన్ నుంచి ఈ 2 రూమ్స్ కూడా సెకండ్ మెయిన్ నుంచి మనం ఆపరేట్ చేసుకున్నాం అనుకోండి సార్, అది మాల్ ప్రాక్టీస్ కిందకి వస్తుందా లేదంటే ఇలా ఆపరేట్ చేసుకోవచ్చా సార్?
చేసుకోవచ్చు, బికాజ్ సప్లై సింగిల్ ఫేజ్ ఏనా.
అవును సార్.
యూజ్ చేసుకోవచ్చు. ఎలా అయితే ఏముంది మనకి, నువ్వు ఎక్కడ మెయిన్స్ ఏది తీసుకున్నా కూడా అది ఎందుకు ఇస్తామంటే మనకి లోడ్ ని డిస్ట్రిబ్యూట్ చేస్తున్నాం 2 మెయిన్స్ లో. ఎందుకంటే ఒకే బ్రేకర్ మీద ఎక్కువ లోడ్ ఇస్తే ఏమవుతుంది, ఈజీగా ట్రిప్ అయిపోతా ఉంటుంది. అలా కాకుండా ఉండాలంటే మనం దాన్ని డిస్ట్రిబ్యూట్ చేసి 2 డిఫరెంట్ బ్రేకర్స్ కి సప్లై చేస్తాం ఆ నుంచి. ఎనీహౌ నీకు మనం సింగిల్ ఫేజ్ సప్లై, మీకు తీసుకునే సప్లై సింగిల్ ఫేజే కదా, మీరు ఎట్లా యూజ్ చేసుకున్నా కూడా నో ప్రాబ్లం టు ఎలక్ట్రిసిటీ బోర్డ్.
Okay, thank you, sir.
Good night.